Good afternoon, everyone. All right, let me try that again. Good afternoon. Okay. This is great. Thank you all for coming here for the Grid of Tomorrow workshop. My name is Arvind Raman. I'm the John A. Edwardson Dean of Engineering here. And I thought I might begin my remarks by giving you a little bit of a background as to why we are here and how this all came together. About a year and a half ago, many of the leaders here at Purdue who work in the space of energy transition got together to really think about what are those areas where Purdue, with its unique strengths, being in Indiana, with our industry partners can do that can project us into national prominence and really help solve big grand challenges. What would those areas be? Because energy transition is a really wide area. And so that led to the start of a Purdue Engineering initiative. It's called LEAPS, Leading Energy Transition Pathways to Sustainability. And I'm going to begin by showing you a video of the Purdue Engineering initiative. Please.
Energy is an integral part of all we do, which makes it the top economic activity driving today's prosperity. Currently, 80% of the energy consumed in the world is derived from fossil fuels. In an era where the eventual transition away from fossil fuels is vital, how can we harness the potential of nuclear energy, capitalize on advancements in renewable resources, and ensure our electrical grids are both expanded and secure to meet the demands of tomorrow? The existing energy infrastructure, developed more than a century ago, has ensured affordability and reliability. However, the additional imperative for sustainability presents an almost insurmountable challenge. But at Purdue, we thrive on challenges, and so we'll turn this challenge into an opportunity, embodying the pioneering spirit of so many Boilermaker alumni who have paved new paths and laid the groundwork for emerging technology. This is our time to step up and bring forth the solutions that will carry us into a new era of innovative energy sources. And this is precisely why we are pleased to introduce the Leading Energy Transition Advances and Pathways to Sustainability, LEAPS, a new Purdue Engineering initiative that marks our commitment to leading the energy transition. The Purdue College of Engineering is reimagining education to prepare leaders who are ready to navigate the technical and societal facets of the energy transition. Just as Purdue alumnus Neil Armstrong's engineering expertise and skilled contributions at NASA enabled the U.S. to fulfill President Kennedy's challenge to reach the moon in 1 decade, it's our next generation of engineers who will answer a new call to transform the future of energy so that it's sustainable, affordable, and reliable. Armed with cutting-edge facilities and intellectual capital, Purdue stands ready to spearhead research that challenges the status quo. Through fundamental studies, we are developing the disruptive new technologies that not only match, but also surpass the value offered by fossil fuel-based systems. In partnership with industry leaders and with our specialized facilities, focusing on mid-level technology readiness, we are transitioning theoretical research to practical, market-ready solutions. As a national hub for scaling industrial innovations, LEAPS will play a crucial role in improving industry efficiency, boosting global competitiveness, navigating new regulatory landscapes, and reducing waste, energy consumption, and emissions. There is no single solution to the energy transition, no magic bullet, but rather a diverse array of strategies targeting specific sectors and geographies. The United States achieved the goal of going to the moon in 1 decade. There is a monumental energy transition challenge that needs to be achieved in the next 3 decades. Purdue is committed to making the steps that lead to monumental leaps in the energy transition. Together, we can craft a legacy of stewardship for our planet.
And the co-leaders of this initiative are Fabio Ribeiro and Lefteri Tsoukalos. Thank you. This is really an initiative that stretches not just across engineering, but across the entire university. In fact, not just on the West Lafayette campus, but also extends to the Purdue Fort Wayne campus. So it is truly a complete Purdue initiative, but that's really rooted in engineering because a lot of our strengths lie there, and because I might be a little biased in saying so, but that is the truth, I think. The reason we started this initiative, as I mentioned to you, was to really identify a few niche areas in energy transition where we could be undoubtedly #1 in the country when we partner with our industry partners. The team got together, did a deep dive into asking questions like, why Indiana? Why Purdue? Why now? What's the value proposition we'd have for all of you? And we came up with about 6 areas that we think we can actually lead nationally in. The Grid of Tomorrow is one of 6 such areas that we have come up with. And our first action in that process is to bring together, convene top industries working in the area together here today for this workshop. Now, what is the purpose of this workshop? What we hope to do out of this, through the Grid of Tomorrow, is really to become a hub for creating talents, jobs, and innovation together with our industry partners here. How are we going to do that? We think there are 3 ways to do that. As we gather together, many industries come together, there will be many opportunities, we think, for business-to-business interactions. Hopefully joint ventures come out of this. Hopefully business partnerships that are going to come out of this interaction. A second key mechanism for getting there is going to be by directly investing in research projects. Maybe one company, one industry here, maybe 2 want to go in together and do something big at Purdue University. Well, this would be a great opportunity to do so. The third is we want to launch a consortium, and you're going to hear about the Grid of Tomorrow Consortium, where we hope like-minded industry partners will try to identify a pre-competitive space where there might be some research involved, but through that entire consortium have access to a wonderful talent pool here at Purdue. And I want to bring this up and remind everyone this is one of the big reasons why you have to consider Purdue as a partner. We are, starting this year, going to be the single largest producer of bachelor's degrees in engineering in the nation. Starting this year, when we count our students graduating in Indianapolis, no other engineering college will be producing more engineers than us starting this year. Now, we're not going to be the largest by enrollment, but what matters more, I believe, is production rate. And so we're producing them faster into the market, so that's really important. And they're absolutely top quality engineers. We are now also #1 by market demand. No other engineering college gets more applications for engineering majors than we do anymore. So it's a really high in demand program. It also means absolutely top quality students, and you had a chance to meet some of them earlier today. And the other thing that's really special about us is the amount of attention we pay to co-ops and internships. We have a really strong co-op and internship program, the oldest co-op program in the country, as a matter of fact. And so all these are really good reasons to be looking for joining a consortium to be able to access those wonderful talents here at Purdue University. And so what we hope to do today is a very public side of this workshop, where what we're going to talk about here is going to be broadcast live on YouTube. There's many people who are going to be watching it online. We had to keep this limited, and it's packed full already here. And we're going to have 3 panel discussions on topics we believe are some of the most important ones to address as we look ahead together to a future here for the Grid of Tomorrow. And so without further ado, let's begin. Right? Let's get started here. I'm going to be the moderator for the first panel, and the first panel is going to be about meeting the rising demand, energy demand. So please join me in welcoming our panelists today. John Kotek from the Nuclear Energy Institute, Senior Vice President. Tim Hanley from Exelon Nuclear, again, Senior Vice President. John McDonald, who's the CEO from JDM Associates, and John is actually a distinguished engineering alum himself from Purdue, and David Whitehead, CEO of Schweitzer Engineering Labs. David, please join us. Yeah, maybe I'm supposed to sit in the middle.
No, I'm going to go grab the head.
Okay, there you go. Welcome, gentlemen. It's exciting to have all of you here. How's your day been on campus so far?
Good.
Yeah. Excellent.
Great tours of your labs.
Yeah, excellent. No, that's great. Well, let's begin with the big picture. The energy landscape in the U.S. is changing really rapidly. With electrification, with the needs from AI data centers, with electrification of industrial processes, some estimates suggest that there's going to be 18% increase in electricity demand in the grid over the next 5 years alone. And people are estimating that data centers alone are going to require 12% of the energy demand of the U.S. by 2030 could be coming from data centers. And the challenge is, of course, compounded by not just the increase in demand on the electric grid, but also by the temporal nature of the demand. We're already hearing stories of how data centers, the dynamics of how the demand fluctuates is different from other sinks of energy and so on. And so this is a really complicated problem. And so maybe at the start, I'd like to ask of each one of you, meeting this rising demand presents a complex challenge requiring us to balance sustainability, affordability, reliability, how secure the grid and the solutions are. So maybe I'd like to hear from each one of you, what do you see as the most pressing challenges from your company's, your organization's point of view as we face this challenge? So let me begin at my right. Dave, please go ahead.
Ooh, can you guys hear me? That is a great and complicated question, and I think if we could solve it right now, we wouldn't even need your consortium, right? It is a challenge. The way I see, at least certainly from the power system protection, optimization, and control that we see, is that things are changing so fast, right? With the integration of new technologies, new generation systems, the visibility, we have wildfires that we're contending with, and what I see our biggest challenge is having a workforce, right, that is capable of addressing these problems. And you know, Purdue certainly can play a very, very large role in it. When I started in the industry, I developed relays and really needed to be a power system protection person. These days, you look at the task of just the protection person, right, that's setting a device to protect a 500 kV transmission line. They have to be a power system expert, an automation expert, a cybersecurity expert, and probably a whole bunch of other things I am forgetting. So the task and the scale with which we're trying to, you know, control and move energy at the speed of light is daunting in and of itself. And so we could talk about a particular technology that we should develop, and that is a point in time, right? Because we're going to invent something else, we're going to need new solutions and stuff like that. So if we have a workforce that is skilled in the fundamentals and first principles, I think that goes a long, long way to addressing any of the needs we have right now, and certainly the future needs going forward.
So a complex challenge, for sure. John, how about you?
I think one of the first things we need to start with is, you know, we focused on generation transmission for a long time, and there's a lot of automation, a lot of information, but distribution part of the grid was not, you know, always had a problem in getting investment. And even today, which is hard to believe, about of the 52,000 distribution substations in the U.S., about 20 to 25% of those are unobservable at the control center, which means, you know, we still haven't automated a lot of the distribution grid. So I think the first step with meeting demand is situational awareness. You know, knowing what is the situation out there, how much information do we have. We typically, you know, we have a lot of applications we want to run on that part of the grid, but we don't have enough data to support those. So I think, you know, the first step, we have a much more focus today on data. You know, our industry for 8 to 10 years now has been hiring data scientists for the first time, applying machine learning, artificial intelligence to transformer, circuit breaker, health information. And I think we need to have the data, situational awareness, look at the behavior of the data. I think we'll have a much better idea of how to handle the demand. And I know there's a lot of emphasis now. The Energy Independence and Security Act of 2007, Title 13, said in detail what the U.S. should be doing with smart grid. And it was after that legislation passed, it was a rude awakening to a lot of us that have been working on the grid for many years, that the end-use customer was now a major stakeholder And we had never engaged with that customer because a meter reader went, read the meter, brought the meter reading back, a bill was mailed, and the payment was mailed. We didn't, and then we started implementing smart meters, and we found unless you engage with a customer, a smart meter project is not going to be successful. So there's a lot of learning we need to do with the end-use customer, meeting demand, and I think a lack of data is one thing we need to tackle first.
Great point. John Kotick?
So I worry about a few things. One, I just worry about we haven't built new generation at the scale that is going to be required over this next decade since like the 60s and 70s, right? So we've got a generation of folks plus who haven't built at the required rate. So getting our supply chains, our workforce, et cetera, our capital is going to be a big deal. As a nuclear person, a nuclear trade association person, I worry about preserving the gains that have been made, including the incentives that have been created to help spur the new build. I know there's going to be a real focus. The president talks about energy dominance. I want to make sure there aren't any unintended consequences as policy changes are made that somehow undermine, right, the momentum that's been built around new generation. And then finally, this is a global marketplace. And so when I think about it, we represent suppliers as well. I worry about what are we going to do to compete and win in global markets, because when you're engaged in international commerce, you are also gaining a lot of influence.
That's a great point. Tim?
Yeah, it's the largest operator of nuclear plants in the country, and just having announced the restart of 3 Mile Island Unit 1 to essentially supply data to Microsoft. My two big concerns, and one goes to what John said, is regulatory certainty. When you want to invest a lot of money in restarting a nuclear plant or building a nuclear plant, you can't have the rules change in the middle. And not as much the Nuclear Regulatory Commission, those are really established, but it is things like the Inflation Reduction Act and what was included in there for new nuclear or nuclear megawatts. It could be with FERC. They just made a ruling at Susquehanna plant that they could not supply strictly the data center that was built there, which was kind of unprecedented. So that regulatory certainty that gives you the confidence that your investment that you're planning on for the next 40 years being a viable investment can't be short-circuited by very short-term regulatory change. And the other one, which kind of fits into that, is the cost. Some of the cost for even building a new SMR gets covered by what's in the Inflation Reduction Act. But going back to what John said about the supply chain, we just don't have that established. And anything that's built one-off is going to be very, very expensive. So I think those two things, the regulatory certainty and the supply chain and the costs associated with that, are my two big concerns.
No, that's great, Tim. And, that's a great segue to the next question. And, John and Tim, I'll address that to both of you. But precisely because of these regulatory uncertainties, on one hand, the need for innovation, on the other hand, we have not seen new nuclear capacity added at the rate, again, to your point earlier, John, that we would have liked to see. And, there are many people who worry about, hey, if that capacity doesn't come online soon enough, maybe there are other solutions we should be investing in, and we're already seeing some of that flowing into grid-coupled storage and stuff, right? And, many other places, for example. So from your points of view, what are some key things that need to be put in place whereby we might actually see really new capacity coming from nuclear power into our grid, let's say by 2030, like in a 5-year time frame? Like, we're seeing all this happen, but it's happening in too slow motion. That's what we see. So, but
yeah, for me, I mean, the big focus has been on small modular reactors, and that came out in part from what happened at Vogtle 3 and 4, the large cost overruns. Those plants are operating and operating well, but well beyond, the time frame and the amount of money that it was supposed to cost. And, one of the benefits of small modular reactors is that they're cheaper to build because they come essentially in modules that are hooked together at the site, easier to deploy. But, one of the things that people have to recognize, if you build one small modular reactor, it's going to be very, very expensive. the parts aren't readily available. There is no one right now that has the forgings to build one of those reactors. And so I think the big thing it's going to take is a multi-reactor order and build them like they do a new subdivision, where you have an order of 40 and you go from one to the next to the next. That's the only thing that makes it beneficial to the supplier to start the supply chain. They have to have the certainty that they're going to have, if they're going to put a new forge line in at BWXT, they have enough orders that it makes it worth their while or the cost of the individual one. So, you know, the recent announcement on AI infrastructure investment, I think is a great opportunity for that. I mean, one of the big infrastructures for AI and data storage has got to be what the power source is. And if you know, some of the estimates can be as high as 55 gigawatts of additional electricity. That's about 180 small modular reactors if they're all 300 megawatts. So that's one of the big things, I think, is you got to have, and standardized design. And when you have every company, the Googles, the Microsofts, all looking at individual designs, you know, if they could get together and pick 1, 2, or 3 and say, we're going to order 50 of these, and then you could, you know, willow down as see which companies are actually producing at the rate they think they could, that would start the supply chain, make some certainty, and get the process rolling. But nobody wants to build the first. Everyone wants to build the 50th. So I think that's the success I think could come out of.
Yeah, and that's such a great point, because when you get to a sustained program of new build in a stable regulatory environment, prices do go down. We've seen that around the world. And that's why China's building 30-plus new nuclear reactors now, because they've gotten good at it, right? And they keep punching them out. And so what we're working on now is, how do we share the risks of those first few of a kind across a range of participants, including governments, state and federal governments. And in particular, you know, Congress recognizes that there's real value in having a strong civil nuclear energy sector in the U.S., both for our domestic needs, but also in those export markets. So what we're seeing is a willingness to at least engage in a conversation around, could the government take on a significant share of that risk? So you don't have a repeat like they had in Georgia with the Vogtle plant, where, you know, ultimately they're worried about ratepayers and shareholders carrying a big portion of that risk. And so we're not across the finish line on that yet, but folks recognize that, you know, certain technologies demand certain types of policy prescriptions to help them get started. We did that very successfully with wind and solar in the U.S. at both the federal and state level, right? Now it's time to do that for nuclear, and I'm optimistic we're going to get there.
Well, no, that's great. Speaking of wind and solar, I mean, as you look at this additional capacity that's needed, how do you see nuclear and, you know, additional renewable capacity like playing off against each other? Or are they different, or are they connected, or how do you see that?
There's a few ways you can do that, and maybe I'll start and then hand it off to Tim, because we were actually chatting about this a little bit earlier. When you look on a system basis, what you find is that when you have a significant share of firm, clean power on a system, if you're trying to drive to decarbonization, that will help you get there for lower cost and with higher reliability than if you just try to do the job with renewables and storage alone. And there's a lot of studies out there that will underscore that. And so what we're seeing is, particularly among these tech companies that have committed to 24/7 clean goals, they're recognizing they have a role to play in creating an incentive for that firm, clean power to come on the grid, right? But Tim, I know you've got some thoughts on matching supply and demand.
Yeah, there's a couple things. One is, when you look at historically kind of the tech companies and the way they would fulfill their carbon goals would be to buy wind RECs, which means they're going to buy RECs from the wind in, you know, West Texas, when their plant may be located in Virginia. And if you look at the rate at which they're using electricity, it does not match the wind demand at the time they're using it. So I think they've come to realize that they really do, like John said, need that firm energy, but they can, you know, fill in with the wind and solar when it's available. But buying the wind RECs in reality doesn't do a lot to lower the carbonization. There are some things we can do. I think the new designs of small modular reactors will be much more flexible in their operation. And so when you do have the availability of wind, that reactor will be able to turn down its power to match the demand much easier than the current plants do. We actually ran into an issue at our Quad City station when so much wind from Iowa was coming through that we were seeing negative pricing at that node. So the plant was actually paying to keep the unit online. We did employ some methods of lowering power, at least so prices came back positive, so we weren't paying to do that. But the older designs were not built to really move power significantly. Most of the new designs have that built in. There's also a lot of other, from a public perception standpoint, most of them are designed that you could have a place where you do medical isotopes, so that's another selling point. So I think combining all the benefits gets the public perception of them much higher than maybe we've seen in the past.
And if I could, for those who are interested in learning more about this, Google has done some really great work. They got a bunch of papers available on their website on the 24/7 clean imperative and how you get there, including the role of nuclear.
Yeah. That's great. Great discussion topic. Nuclear is one part of this big jigsaw puzzle that we'll have to put together in the next coming years. Let's turn to another key part, which is obviously something we'll have to think a lot about, which is grid edge technologies and what's going on there, whether it's rooftop solar, local power electronics that are set up at the edge of the grid, energy storage at the grid edge. And John, you were in San Diego recently at the IEEE Grid Edge conference. In fact, if I understand correctly, you were moderating a panel much like this one on AI approaches to grid edge asset management, right? So can you summarize for us, like both in front of the meter, behind the meter, like what's going on that we need to be aware of as we try to deal with this grand challenge, at the edge of the grid?
Yeah, this is a trend that is going to only continue to grow, driven a lot by integration of renewable energy on the distribution part of the grid. But it's, the philosophy was always centralized control. We didn't have anything at the edge of the grid. We actually we had very little in the substation for a long time. So all the data went up to the control center and all the analysis was done there. And then in time, we would distribute applications at the substation level and now at the edge of the grid, okay? And one example that I wrote an article in Power Electronics Magazine in 2013. It was a situation in California with San Diego Gas and Electric where policy changed that incentivized homeowners to put rooftop solar panels on their homes. And the policy was so attractive, and this one feeder fed very affluent homeowners. These are homes along the Pacific Ocean. And so these are homeowners that could afford to put the rooftop solar panels on. And all of a sudden, almost overnight, over 35% of the homeowners on one feeder installed rooftop solar panels. Well, the online tap changer in that substation is a mechanical device supposed to keep the secondary voltage constant as the primary voltage fluctuated. It was operating 5 times, 10 times per day. All of a sudden, over 35% of the homes have rooftop solar panels. There's a marine layer of fog over the roofs of these homes in the morning from the ocean, and as that fog burned off, all of a sudden, all the homes began generating at the same time. At the edge of the grid, what happened was the voltage on the low voltage network spiked unbelievably and then oscillated because there were still clouds going in between the sun and the panels. This tap changer in the substation was operating now 150 to 200 times per day. It's a mechanical device. Its expected lifetime went from 35 years to less than 2 years. So the article said we need, for the edge of the grid, we need power electronics expertise, and I preach this at universities, power electronics researchers and professors to work closely with power systems because we have new applications of power electronics in the power system on the electric grid. And as the penetration of distributed energy grows on the distribution part of the grid, the volatility of voltage and reactive power is only going to grow. And mechanical controllers for the future grid just aren't feasible. They wear out, So in the article, I wrote about 3 applications of power electronics. What's interesting now is, and one other point in terms of trends is the typical smart metering companies that have all the demand data, the customer data, were typically, they kept that data and used it themselves. They had a meter data management system, that would have applications, but it was down basically at the customer end and kind of siloed within the utility. What's interesting in the last year now is smart meter vendors are signing agreements with SCADA vendors. So in other words, the control center vendors that have the data upstream of the meter, that's valuable data, but it's never been connected with the customer data. Now you have Itron, who's signed agreements with 2 SCADA manufacturers. You have Landis & Gear that's hiring grid expertise to expand. So what we're seeing with is more end-to-end look at the grid, bringing the customer data together all the way upstream to the control center, combining that together, and to say what are the new value propositions? What's the new value that I can have if I have an end-to-end look at the information? And this is just starting, so it's really exciting. We don't know what all those value streams are yet because it's very new, but it's just going to grow.
Thank you, John. As a mechanical engineer, it always breaks my heart to hear that mechanical solutions don't work anymore. But as we think about modernizing the grid, increasing the capacity, there are many new challenges that come in. One is going to be about, especially in this era of geopolitics, worrying about security of the grid. It's really important. So Dave, let me turn to you. Schweitzer Engineering is a leader in this area, especially when you look at next generation, digital monitoring, high frequency monitoring and control devices, certainly not mechanical, for the grid. What, as you look to the future, what innovations are needed in the monitoring and control side of it that will not only help in a more secure grid as we see this increased, 18% capacity we're looking at, and what are the key drivers that are forcing those innovations to come out?
I think when we take a look, we could be here for 2 hours talking about all the challenges / opportunities that are presented before us. But utilities and a lot of us have this speed and scale challenge to deal with, right? It is, we need to do a lot more, a lot faster, and then once these devices are out, how do you manage all of the relays or their voltage regulators or cap bank controls or whatever they might be? And so some of the challenges we're seeing if on the protection side is there's a lot of integration of IBRs. You were talking about the rooftop solars. Those represent a different challenge. They're not a big spinning mass anymore where the generator pushes a bunch of current into the fault. That's pretty easy to detect. Now we have these IBRs where there's a control loop that somebody, computer scientists probably generated how the IBR should behave when in a fault condition. So detecting faults is becoming a lot more trickier than it was before. So looking at transients as opposed to just steady state fault current, if you will. There's a lot of work going on there, whether it's incremental quantities or time domain technologies or what have you. John, you were talking about visibility into systems with the integration of IBRs and the power quality challenges that perhaps they present on the power system, and can have enough resolution of the measurements that we're taking to actually understand what's happening out in the grid, right? A SCADA system that's updating, say, once every 5 seconds, right? These days is like driving down the freeway at 70 miles an hour and opening your eyes just briefly every second or every 5 seconds, right? That's no way to drive your car these days. Well, or any days maybe, I don't know. So having sensors, a lot of stuff we're seeing now is this. If everybody read PES this month, the January, February, is all about streaming data and what you can do with it. So everybody probably knows about synchrophasers, but that's so 2000s these days, right? It's a very bandpass signal with a magnitude and an angle. Now we're looking at synchronized measurements where we can bring this data in at not only, I think synchrophasers, the fastest is 60 times a second, once every cycle. Now we're moving into 3 kilohertz, 10 kilohertz. We even have megahertz streaming data, really having this high it's essentially an oscilloscope now on the power system where we can see what's going on. That's our first step. Now, once we understand what's going on, then we can take control actions to take care of power quality problems or transients or what have you. Other problems that are, out on the West Coast, we have wildfires, right? And detecting a down conductor is a really, really hard problem. I think there's been a lot of great work, probably 40 years ago, started at Texas A&M. But having a wire on the ground detecting it is really, really a hard problem. And now we have power quality issues with IBRs, not issues, but challenges kind of stuff. And to detect a down conductor, we use things that aren't 60 hertz based, right? And so these things are competing against each other. So there's a lot of challenges there. And finally, you can start putting sensors out all in the power system, as John was pointing out, so we get a really good understanding to optimize the power system, to put it in a really good state during steady state times, but also during abnormal times. And all that's going to require communications. There's some really good stuff going on with like point-to-point communications, but LTE and even private LTE for utilities, which I get really excited about. Of course, we're going to hook all this data up and it needs to be cyber secure, right? So one of the activities that we're certainly looking at is what is inherently cyber secure, right? We keep putting Band-Aids and Band-Aids and Band-Aids on our present communication systems, and every day we open the Wall Street Journal or CNBC, right? And we learn about yet another hack or something like that. So at some point, we just have to say, let's stop. Let's design a communication system for, OT systems or critical infrastructure that is really built from the ground up to be cyber secure, to allow us to share all this information, to be able to manage and control our power systems.
Yeah, please go ahead, John.
Dave brought up communications, and I don't think we put enough emphasis on communications. I always say communications is the enabling technology that allows us to automate. Without communications, we wouldn't be able to automate. And I always say, at the beginning of smart grid, what I would say is, before we jump into smart grid, let's make sure we have a strong grid. Strong grid before smart grid. Strong grid is the communications infrastructure and the IT infrastructure. Because I see many utilities, they get budget money available and they want to buy new things and they implement it and they don't get the performance they expect because of problems in the communications infrastructure. Mm-hmm. You're layering new things on top of communications infrastructure that has old technologies that haven't been updated or should be replaced. Strong grid before smart grid. And the other thing is, when we go to distributed intelligence in Grid Edge, our communication system was optimized for top-down communications, because all the data went to the control center, and then everything, all the changes and control commands went downstream. If we're going to do control center-based, substation-based, Grid Edge-based, we got to rethink the communications. Dave said point-to-point. Think about peer-to-peer communications. If I'm at the substation level or at the grid level, and I want to optimize, I want to make a decision at that point. I don't want to have to go back upstream to carry out the control command. I may need not only information where I'm located, but at the neighboring grid edges or the neighboring substations, and I don't want to have to go upstream to get that. I should have that readily available. That's the communications infrastructure we have today isn't optimized for that. It's optimized for top-down. Mm-hmm. So we have to rethink, I think, foundationally, the communications infrastructure to support more of a distributed hierarchy.
That's a great point. That's a great point. I'm going to ask the audience to start thinking of questions they want to ask, because I'm going to have one last question to each one of them, and then over to the audience for your questions. As I mentioned earlier, there's good reason to be here at Purdue. The talent pool here is absolutely phenomenal. As you look to the future at all these challenges, your businesses are all going to grow. Hopefully they grow a lot. This is great. But what kind of human resource talent needs do you think is needed today? Is the same power systems engineer going to be enough? Is the same, like what would be the profile today of a really successful kind of hire that's going to help you get there? And what should we be thinking about doing at the university now to help prepare the talent? So, as you set up as you get your 120 SMR order in place, like what you want to have talent ready for it. What do we need to be thinking about and doing now to prepare for that? So maybe let's begin here with John and Tim, and then over to you guys.
So when we think about the talent, you know this better than I do, right? We use engineers, of course, all right, but we actually don't use all that many. You ran nuclear power plants. I'll let you talk about the other types of folks we need in the industry. What I would just say is we're going to need a lot more of all of the types of workers that we use in the industry. They come from a bunch of different places. To the extent that you all can, of course, continue cranking out great engineers, but also help get other people excited. I mean, there are a lot of folks out there that might not, come through a 4, 6, 8-year degree program, but we're going to need them too. And I'll let you talk about some of the types of folks we're going to need.
Yeah, John mentioned, if you look at the workforce at the existing nuclear power plants, only about probably 20% are degreed engineers, but that certainly is in high demand in quality engineers. I would say a focus when there is people that know cybersecurity and digital type of electronics, which the current workforce that may have started there in the 70s and 80s didn't have. So I think that's one thing if you're looking as a student, you may be a peripheral thing to study if you're going to be a nuclear engineer, mechanical engineer, electrical engineer. But the majority of the workforce there are building trades type of people. The mechanics, the electricians, the instrument control technicians, those are the things where it's actually harder to hire them. And I know Purdue has a relationship with Ivy Tech, right, that is a great source of that, where they can provide training as a welder to get a certificate as a welder. They can train INC technicians. And certainly if we're going to build 100, 200 small modular reactors, those building trades have got to be in place, because that may be the limiting factor on building them. Even though they come in modules, ultimately you got to weld them together, and you got to connect the wires at the plant. So, that's I think the big pinch point, and there's just not a lot of people going into those. But again, as mentioned earlier, it's a different electrician than it was 50 years ago. It's not somebody that would wire your house. There's a lot more that goes into the electronics at those stations, and the SMRs even more so will have more of that, digital intelligence, as opposed to I'm just hooking this wire up to this lug type of thing.
Yeah, and the one thing I'd add, just as somebody who spent most of my career in the Department of Energy and the National Lab System, keep cranking out those great master's and PhD students, because whether it's the labs or whether it's the companies involved in this cutting edge research, maintaining our competitive edge is just going to be so important going through this century.
Gotcha. And Tim, to your point, indeed, we have a great partnership with Ivy Tech, the nation's largest statewide system of community colleges. We work really closely with them, actually. That's another really good to be thinking about Indiana as well. Let's go over to Dave and then John.
Are we just focusing on what Purdue can do for us?
Well, higher education is just broadly, what do you see as the workforce need? And maybe it's universities, higher education institutions, maybe it's community colleges. Where do you see that going?
We need them all. And I especially appreciate your comment on technicians and the technical trades, right? It is, I think we suffer greatly here in the U.S. Try to get a plumber to come to your house or an electrician, right? It's nearly impossible. But if we're focusing on the university side, you have a limited amount of time with your students, right? 4 to 5 years, and as a consumer of your product, if you will, what I would request from the university, what I think you do the best service for us as the customer, is be teaching the students really the fundamentals that don't change, right? So for us, Maxwell's equations and F equals ma and those kind of things. If we get too far off of chasing a shiny object or something like that, I don't think we're doing our students any benefit from doing that. But focusing on those things are going to change. There'll be a new programming language. As an employer, I'll teach you how to do that stuff, or design or something like that. Every company's going to be a little bit different, right? But the things that like Maxwell's equations or F equals ma, those kind of things. If a student can come out of this institution with a really strong understanding of those things, they can succeed just about anywhere with any company they go and work for.
That's great. Stick to the fundamentals. John, what do you think?
I think of two things. One would be the days of the specialists are really over. So much of what we do is interdisciplinary. I think we've all talked about that. From a Purdue point of view, like one example I gave was power systems and power electronics to work more closely together. Another example is data scientists working closely with power system. You know, we're hiring so many data scientists who know nothing about the grid, and we're teaching about the grid. In my panel session last Thursday at the Grid Edge conference, a data scientist from Encore in Dallas, Texas, said, not only are we teaching data science about the power system, she is leading courses within her utility of teaching power system people about data science. Okay, so the world, you know, if I was a student now, I'd try to learn as much as I could about as many related areas as I could. I would have much more value to the workplace in doing that. Second thing is teaching. Every course should be taught where teams of students have a problem to solve and they work together. I know CEOs of companies who say, when I interview a student, they could have the best GPA, lots of internships, a lot of extracurricular activities, but every answer to my question, if they say, I did this, I did that, I was the one that did this project, I was the one that, this wouldn't have been successful if it wasn't for me, I don't care how good they are, I'm not hiring them because they're not a team player. And if I hire them and put them on with a team of people in my company, they'll destroy the team effort. So we should teach students how to support a team, how to work as a team player, how to solve things. And the team is interdisciplinary. So this is where you get into working with people with other specialties. But you have to have a team approach. You know, you have to, if there's somebody on a team that's not working as well as others, you work with that person to bring them up. You don't criticize them, but you want the whole team to be successful. And I think that's something we miss. The courses I took at Purdue, where we had a technical problem at Commonwealth Edison in Chicago, in a fourth-year power course, and we had a team. I had a team of people, and we used the Purdue staff car to drive to Chicago, and we met all day with the ComEd people as a team, and then we came back and solved that problem, presented the class. That is the way you can better prepare, be better prepared for the real world, if you're taught that way at Purdue.
Gotcha. Well, thank you, John. Jill, how much time do we have for questions? 8 minutes for questions. So let's turn it over to the audience for any questions you might have. We've got a mic going around to ask questions.
So maybe this, John, this is to you. As we think in California, obviously we have retired a lot of fossil generation, and you talked about the issues around inverter-based systems, renewables. As we see that, we're in the process of putting a lot of StatComs and SVCs, but how do we incentivize, how do we get access to some of those inverter-based systems that were there designed with the renewables for the local voltage control as well as stability, but using it for the bulk electric system. And now you compound that with basically the data centers and the hyperscalers where we're seeing the reliability issues there. So how do we think about managing the grid, the bulk electric system, you know, with all of the inverter-based systems that we have? And we're seeing it in California now, and I don't know that we can put in enough SVCs and StatComs to keep pace. So I'd love to have your thoughts.
Yeah, and Dave also. I would say a couple things. One would be, you're right, we have a lot of islanded control systems that are working to their own optimums, but there's no regional optimum, you know? And microgrids, we're putting microgrids in, they're optimizing the individual microgrids, but Commonwealth Edison with 5 microgrids, we're now working on how do we coordinate all 5 to benefit the utility, because the optimum of one individually may not be the best optimum for the region, right? So we really need to think more. You know, when I teach, we try to teach students, see the big picture. Don't just stop with a microprocessor-based device, but look at the big picture and what's the optimum for the big picture. So we don't want islanded control systems that are working with their own local optimums. We want to coordinate on a broader scale, because then you have a system optimum. So I think I think the viewpoint has to be different. We still have a lot of things, legacy and existing, but as we, you know, if we can try to coordinate those together. But as we implement new stuff, let's think of the big picture.
I know that we're talking about local and global optimization, right? This is like, I'm glad I'm back on a university. It's kind of fun. Maybe I'm going to enroll when we get done here. To your point, and John's, I think a lot of the challenge we have right now is we come up with a solution as a point solution. I'm going to put rooftop solar on my house, right? And neglect the facts like, what's this going to do to the voltage regulator that's down the thing? I'm sure that voltage regulator, right, was designed for a single direction feeder, right? Power only flowing one way. Then we put rooftop on there. I bet that the regulator doesn't know how to tap up when the source is actually now on the other side of where it thought it was going to be, right? So when we start thinking about, hey, I want to put rooftop solar, and what am I going to do with the voltage regulator? What do I do with the cap bank control? What am I going to do with the feeder protection? You were talking about, back when I started in the industry, all the cool kids were in transmission. Distribution systems are probably one of the most complicated things with bidirectional flow, right? Sources everywhere. It is just a fascinating place to be in right now, right? And getting back that we need to treat things as systems, not just as single products or entities, if you will.
Great questions.
I'm moderating a panel in a bit, but I can't help but ask a question now. So your all's focus in particular was on this demand for new generation, and I think you've done a great job of articulating a lot of the technical barriers and workforce barriers. But another thing I wonder if anybody has any comments on is the cost. As we think about building out the kind of generation that is required, not just for hyperscale AI, but just the onshoring of industry and other things that may demand electricity, such as electric vehicles, the cost of this is really significant. How do you see new creative ways to address that? And can ratepayers, in the sort of old way of doing things of putting it onto the rate base, is that going to be realistic when you're talking about billions and billions of dollars in new investment that has to be financed?
I think there's different ways to look at who's going to do the build out. So if it is, the Oracle, SoftBank, those groups that just came out with this $500 billion investment, they're not a utility, and so that doesn't go into the rate base. And those companies, and not those in particular, the big tech companies, seem to be much more interested in decarbonization and showing that they're, zero carbon footprint. So they're willing to pay a premium. I mentioned this a little bit earlier. No one wants to build the first because it's expensive, but the 40th is less expensive. If you could get a group like that together and dollar cost average the cost of all of those units, regardless of where the first one is located, is one way to bring the cost down, and the cost will be coming down. The other thing nuclear gives you, small modular reactors, what's going to be built that really supplies it? It's either gas or nuclear. I mean, those are really the only two choices. Nuclear gives you a pretty steady cost, dollar cost average over the life of the unit, because there's a certain top price of uranium, because there's a number of uranium mines in North America they've shut down, that when the price gets to that level, they'll start them back up again. So you know what your fuel costs are going to be over a long period of time. When Russia invaded the Ukraine, natural gas went from $2 a therm to about 11 overnight. So natural gas has some fuel volatility concerns that aren't a concern with nuclear. So I think the big part is you need a big order to get the supply chain so everything's not a unique piece of equipment, and dollar cost averaging the construction cost, whether it's the tech companies or a number of utilities. Co-ownership of nuclear plants is not a new concept. That's been going on forever. Would bring the dollar cost average, but what everybody always asks is, if I'm going to build an SMR, what's it going to cost? If you're going to build one, it's a lot. But if you're going to build many, I think the price naturally comes down as you become more proficient. You get the building trades that will go from plant to plant to plant, become more efficient in building them. That's what I think is how you bring the cost down. And again, the fuel cost certainty over the period is much more stable than natural gas. And natural gas may be low for a long period of time, but there is that instability factor when other, if there's a fracking accident or some other global conflict. So I think there's some trade-off in knowing what your fuel cost certainty over a 40-year life would be, than a natural gas plant. But I think it's going to be a mix of both.
Yeah, and just to harken back to a comment I made earlier, I think this is why it's so important to retain the incentives that have been enacted over the last several years. You know, the way we got to the wind and solar build-out we have in the U.S. is through state and federal incentives, right? And something like that is really, it certainly energized the conversation around new nuclear in a way that just didn't exist just a handful of years ago. And that sort of smart policy doesn't need to go on forever, but it's going to need to go on for a while to get over that early of a kind hump.
Great point. 4 minutes. Time for Andrew. As we wait for the mic to get to Andrew, I did want to do a quick shout out to the co-leads of the Grid of Tomorrow Consortium. Dionisios Aliprantis is there and Andrew Liu. Thank you both for being here. Over to you, Andrew.
Right, thank you. Question is still about the nuclear. So you mentioned about building like 50 SMRs that are going to be cost effective, but 50, my understanding, like SMR, the capacity is like between 100 and 300 megawatt. So 50 of that's a huge load. That's going to be co-located with data center, or if not, then do we have the transmission infrastructure to connect that? And also, in addition to data centers, what about the prospect for serving hydrogen? So,
so certainly with respect to hydrogen, yes, we've seen a lot of interest in that. Frankly, there's been some issues with the way that the previous administration went about implementing the hydrogen tax credit in the law that initially seemed to restrict what would be eligible. They've expanded that a little bit. So I'm going to be really fascinated to see how those hydrogen hubs in particular move forward and whether the demand does in fact get created. In terms of the construction of the nuclear, one of the great things about nuclear, particularly some of these smaller designs, is you've got a lot of flexibility in terms of siting. I mean, you can't build them everywhere, but you got a lot of options. And so, the ability to build close to load is one of the things that helps nuclear from a systems cost benefit, have a real advantage because you can avoid the need for the long distance transmission. So we do have a lot of folks now looking at, where can we co-locate nuclear generation and the end user.
Yeah, just to be clear, I was never talking about trying to build them all in one location. I mean, some of the designs don't even require a large body of water for cooling. There's air-cooled. So, I mean, some of the former restrictions where you'd build a nuclear plant was always near a large body of water no longer apply. And there's great advancements in technology on the secondary side of the plants where the majority of the cooling really has to take place that leads to much greater efficiency, so much less water use and the ability. It's much easier to inject 300 megawatts than 1,200 megawatts, which is what a large PWR would be right now. So I think that flexibility is one of the prime benefits of an SMR.
Well, that's great. Well, we are at time. Will you please join me in a round of applause for our great panelists here today? Jill, do we have a little break before our next panel? We'll return at 2:30. Thank you all. You can stretch your legs. Thank you all for being here. Appreciate it. That was great. Tim, I had a question for you.
Yeah.
Thank you, John.
All right, I think we can go ahead and get started. Are we good, Jill? We're good? All right. Well, thank you, everybody. I'm Paul Mitchell. I'm president and CEO of an organization called Energy Systems Network. It's a 15-year-old nonprofit that's based here in Indiana, works with a number of industry and academic and government institutions, and we're always happy to be here at Purdue. We're honored to have President Mung Chiang as one of our board members. We've got a great panel here. It's a large panel. We got a lot of leadership here. So I'm going to do a quick introduction, and I'm doing it in the order that's here, not necessarily the order that you all sat, right? So let's start with William Jefferson, EVP with NiSource, Matthew Gardner with Dominion, a VP at Dominion, Nick Nation from Mid-America, Joe Bentley with Indianapolis Power and Light. No, I'm sorry. That's a different era. He and I have been catching up. With PG&E, he's a senior vice president there, and Todd Ramsey, senior vice president of MISO. And of course, I know MISO well. John Baer, CEO, there's the chair of our board, so important contributor. So the title of this panel is Shaping the Future of Electric Power Systems. We're going to try to think a little bit further out than even the last panel did. So we're looking at kind of a 10 to 20 year time horizon. And so as we talk about these topics and I ask questions, I just challenge the panelists to think not only about what's right in front of you today, but kind of how do you see those challenges playing out over a little bit longer time period. Let's start with this. We're going to do things a little bit differently here. We're going to do kind of a rapid fire answer attempt here anyways. So I'm going to ask everybody the same question, try to keep it concise. What does a modern grid look like to you in 10 to 20 years? And I want you just to say, what is one thing that you think in the next 10 to 20 years is going to be a big game changer or something new or different that maybe people aren't necessarily thinking about? And it doesn't necessarily have to be some wild technology. It could just be, transformers. You get to start.
I gotta go first?
Yeah.
Thank you, everyone, for the invitation to be here today. It's good to be back on campus. 10 to 20 years from now?
Yep.
Okay, so we can get out in time where new technologies potentially have an impact. So the previous panel mentioned the promise of SMR technology. I agree. 10 to 20 years from now, that'll be a big part of a successful future that we're all trying to plan for. Other new technologies I think are going to play a relevant role in that time frame is long-duration storage. We have short-duration storage deployed today in the industry, and we're seeing the benefits of 3, 4, 5-hour storage. Solves quite a bit of problems that we face today, but there are problems that are 24-hour problems, even 3, 4, 72-hour problems that I think long-duration storage has promised to help us address as well.
All right, so we got SMR and long-duration storage. By the time we get to the end, everything will be taken.
Vaporware.
No, I'd echo that as far as appreciate the invite. Great to be here. I have a little bit different perspective. My day-to-day role is really heavy in distribution operations, and when I look at the future, I really resonated with the comment earlier about just the visibility into the system. So, the additional sensors, the meters, being able to utilize that information is just going to be huge. And I think that's great for our control room as we get more visibility into our substation and on the distribution system, but getting that in the hands of our front line as well, I think that's a really important aspect that I think that, we'll see future down the road.
I will echo the thanks. I'm Matt Gardner, Vice President of Electric Transmission at Dominion Energy. And I'll take a little bit of a transmission or a macro level grid view in my answer, which, by the way, 2 wonderful answers. And if you looked at my notepad from the previous panel, it's just yes, 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 underline. Great panel. Thank you very much for opening us up and stealing all of the thunder that I could have possibly have ever. I'm just an imitator of John and David and others. But anyway. But what I think the future of the grid looks like is certainly a full realization of the digital substation that we're starting to see emerge now, but going beyond that towards fully leveraging modular, prefabricated, pre-engineered infrastructure for the deployment of our grid. I'm thinking of leveraging like gas-insulated switchgear with whatever future gases we end up migrating to, and having substations that come in a box and bolt together like Legos, as opposed to substations that are stick-built as they are today and wired with 2 to 3 miles worth of copper. So I think we'll see a lot more modular, prefabricated, pre-engineered. I'll unpack a little bit more on that later in the panel, but that will pair very well with the foundation work that is being laid right now in the digital substation. It'll help us address the capacity problem that we have, and also the capability prospect that we have, while also giving us levers to not only help address the expansion of the grid, but also adding resiliency. If I've got Lego bricks as grid elements, then if I have a problem, whether it's a natural disaster, God forbid, a terrorist attack, then I can just go back to my Lego bin and rebuild the grid back. And I think all of the elements for making that a success exist today. and we'll come together over the next 10 to 15 years.
And there's a lot of other industries doing it.
Oh, yeah, we
Look
are.
at
We
the
would be a
automobiles
jump-
are coming off an
Yeah.
assembly line. They are as complex as a transformer.
And
let's be
John,
honest.
mentioned, SMRs.
Yeah,
modular.
we can do it with nuclear, then
We're
we
doing
can
it. We're doing it
with,
on the energy side. We need to do it on the wires and substation side.
Good point. All right.
All right,
William.
Bill Jefferson, nice source. I think everything these guys have said, even magnified. I think data, utilization of data, integration of the system through data is going to be the big change. Right now,
And
we're
do you think
starting.
AI is going to be a part of that in-house?
AI is absolutely a part of that. As we build out the system now, we're adding the ability for the system to be seen and heard, and we're going to eventually tie all of that together with the generation piece to get better utilization of everything we have. But it's going to take time, that 10 to 20 year period, to get all of those sensors and modules out. I think that's the key.
Joe Beltney, PG&E. I would be remiss not to say when we first started this discussion about this Grid of Tomorrow Consortium, which that wasn't the name at the beginning, was about a year ago. And I just want to step back, and it was the dean and my head coach, Patty Poppy, will be here shortly, was their kind of brainchild to say, let's get the industry together, let's get utilities, let's get vendor partners, let's get customers together to really talk about what it takes. And I am super excited about seeing the culmination after a year and seeing this, and we're actually seeing this as not the end, but the beginning of this opportunity. So can't thank Purdue enough for that. I would say yes to all the folks. Distributed resources. And when you think about California right now, between now and 2040, it's going to double in size, going from about 80 gigawatts to about 160 or 170 gigawatts of generation. You think about that. 7,000 megawatts a year needed to be able to meet the demand. We're going to see about 4 times as much transmission, high voltage transmission needed in California. So we need it all. And so ultimately today, we need to be able to leverage the distributed resources there, optimize, orchestrate those to be able to deliver, because we need it all in California, and I think we're going to see that throughout the entire industry.
The next question is actually going to get into that, but as the moderator, I get to give my idea on this as well, right? So one thing that I think maybe we need to keep our eye on closely, and we know this is happening in other countries, particularly in China, is actually the use of robots and drones and other automated systems to ensure that we have a grid that's functioning right. And so, that data that we're talking about, the collection of that data from remote locations, the fact that we have a workforce challenge and that some of this work is dangerous, including nuclear technology. And so by 20 years, 20, 30 years, we may be pretty far along in some of the AI and robotics. And so I think there's probably a role for advanced robotics and automated systems, drones, ground-based vehicles, et cetera. Joe, actually the next question is really for you to build on what you just talked about. It's this integration of renewables and distributed resources. And so I think it's interesting because it's happening in California. It's been happening in California. It isn't necessarily happening everywhere else. I'm familiar with some of us in the industry. Know some of these FERC orders. FERC, am I getting it right? 22222. It's a bunch of twos in a row. And that sort of gives instructions to the MISOs and the PJMs of the world that, hey, you're going to have to allow aggregation of distributed resources down to the individual homes and businesses, things behind the meter. It seems like that's been a conversation, at least since I've been in the industry, which is 10, 15 years, but it's really happening in California. So what is the status of it today? And then what do you think that looks like 10 years from now? And do you think it can really play a meaningful role in reducing the need for large-scale new generation?
Yeah. So let me give you some numbers for Northern and Central California. So at PG&E, we have roughly 900,000 rooftop solars in our service territory. Okay. We have nearly 700,000 electric vehicles driving around Northern and Central California. Think about that. About 1 in every 5 EVs is driving around Northern California. Think about it. We have 120,000 stationary battery systems in our service territory, okay? Largely put in there for reliability and resiliency. But just think of the capability and the capacity that reside, you know, in those EVs, in those stationary systems. And so we are incredibly bullish about the opportunity of distributed resources. And as we think about this, and I think the panel before talked about affordability, as we think about delivering for our customers at the lowest societal cost, that's got to be a part of the equation. We've said at PG&E, at the end of the day, you know, that we have those devices at the edge right now. And so how do we orchestrate and optimize that? We think there's a role for the utilities because we're not out to be a profit maximizer, okay? We truly want to deliver energy at the lowest societal cost to customer. And to deliver 7,000 megawatts of generation, we're going to need those grid edge devices to be able to do that. And so as you think about the future of us to be able to really manage that, DERs have to be a part of that equation. We've been working with the auto manufacturers. Obviously, I think we have one of our customers, you know, that we work with Tesla here, the auto manufacturers. We've been working with our partners at Schweitzer and Schneider as well as how do we leverage that to really make that part of the equation. And so in California, it's here. It's not coming. I guarantee you it's here, and it's coming to a utility and an area near us as well. So that's what I would say.
Matt, do you want to comment from a different service territory and a different, how do you see the distributed resources playing out from a Dominion perspective?
Yeah, our view maybe rhymes with yours, but is a little bit different. We definitely see an all-of-the-above approach. So certainly we'll see things happening behind the meter on the customer side, distribution-based, a continued integration of distribution-based resources on our grid. But we also have one of the most active queues in the PJM RTO for transmission-connected resources. Many of those resources are inverter-based renewable resources, but we certainly foresee the need for firm dispatchable resources as well in the future. As I mentioned, that does include all of the above. Certainly there's nuclear in there, plans for a number of small modular reactors in the Commonwealth of Virginia, and then also gas as well, natural gas. So that's kind of what's playing out. What the landscape that sets out for us is one of a dual front challenge within the Commonwealth. Significant load growth in the DOM zone, as PJM likes to refer to it, 5.6% CAGR load growth. That's going to essentially double our load as well in the next 15 years. So that sets up the dual front challenge that I was talking about. The infrastructure needs are servicing both record-breaking growing load, and in our service territory, that load, the drivers behind that load growth are data centers. We serve the world's largest data center market. They refer to it in the data center business as Data Center Alley. It's roughly a 35 square mile area that is situated north of Dulles Airport, if you're familiar with Northern Virginia, centered around Ashburn, Virginia there. Significant market, largest in the world, larger than the next 5 markets domestically combined, larger than the next 4 international markets combined. So that's what's driving our load growth. That dual front challenge sets up a tension. It sets up a tension at the transmission level, where if you don't address that, you're going to end up getting constraints. And so we're working on developing the capacity at the transmission level in order to alleviate constraints that have emerged and also insulate or ensure against the emergence of future constraints. How do we do that? How do we address the capacity problem? Certainly it involves everything that we've already kind of discussed up and down the panel today, both on the infrastructure side, but also on the data side, making smart investments in iron in the ground, wire in the air, but also leveraging data, as has been mentioned, to make sure that we optimize the operation of those assets. A good example of how we're doing that is, and I'll stop after this, a good example of how we're doing that at Dominion Energy is realizing that we need room to explore the data that's coming in, to innovate with the data that's coming in, to test the data that's coming in, and then to move it into production. And I think one of the ways that our industry has struggled in the past with new types of data is we rush to a use case. And that often means rushing the data into the hands of someone who is not prepared to consume it, right? Think of any idea that you try to rush into production. There really is a change management process that needs to be defined. And when you start trying to rush a new tool into an operator's hand, whether it's in a distribution operations center or a transmission system operations center or even a network operations center, if you try to rush data and tools into that environment too quickly, then all of a sudden the use case tends to unravel on you because of simple things that could have been prevented if you had been able to live with that data, play with that data, imagine with that data. And so to that extent, we've developed what we call a monitoring, analysis, or restoration center, which is a center that looks an awful lot like an operations center, but it's purely focused on decision support and situational awareness for real-time utility operations. That's helping our field technicians understand what's going on in the grid, helping understand what these alarms that are coming into our system operations center mean. If you and so forth. I can go on and on about that, but there is really this tension. It's not just an infrastructure tension; it's also a data tension, and you really need to have a place where you can manage the change and the evolution of those use cases into what will one day be a polished and ready product that your operators will find used and useful, and will have the appropriate training experience to leverage.
So you brought up actually kind of good segue into the next topic, which is integration of data center demand. But I want us to think about this a little bit further out. And you mentioned this word tension. We can see already the tension that's coming from this emergence of a completely new customer. And actually for you guys have been dealing with data centers for a long time, because Data Center Alley has been a key location for, let's call the first generation of data centers, which is more about cloud computing and data storage. This idea of hyperscale data centers, just to put it into context, just here in the state of Indiana, and obviously we know this is going on across the country, there's 5 different hyperscale data center sites that have been announced. Whether all 5 get built, we'll see, but all 5 of them have aspirations to be a gigawatt, right? So it's 5 gigawatts of load. Indiana's peak load is around 18 gigawatts, give or take, maybe 20. So it's a huge increase. And they want to go. They want to build these things fast. The tension is that consumers, which has really historically been the lifeblood of the companies on the dais here, is they're sort of looking at this, okay, I like AI, I think. I like AI. I don't know yet for sure. I might be a little bit scared of it. But I don't want to see my bills go up, and I don't want to see huge infrastructure projects because I want maybe more of the distributed resources that you're talking about. I'd like a little bit more control. And so the question I have is as we think about the emergence of data centers, do you see them as being a catalyst for almost an idea of maybe it's not a one-size-fits-all grid, in the sense that for the last 20, 30 years, we've sort of said, well, when we build generation, it's the same thing for big industrial consumers that need 300, 400, or 500 megawatts, and the individual consumers benefit from it too. Can you see the way energy is consumed and used in urban and suburban environments among houses and individuals, taking a different path than, say, the grid system that's needed to support these big AI data centers as well as other large load consumers? So talk about what MISO's looking at from the standpoint of these large loads coming in. You mostly deal with the large loads, but then maybe as others react to the emergence of these large loads and the policies that are driving those, is there a tension there with taking our eye off the ball of what the mom and pop shop or the individual homeowner might want or need in the future?
Okay, let me give a little overview of MISO for anyone who's not familiar with what MISO does. We coordinate the operation of the bulk power system, the combined transmission and generation system across 15 states in the Midwest and Mid-South part of the country. So the middle of the Eastern Interconnect, from the Dakotas down to Louisiana. Now, as a power system operator, we don't own any of the assets that I'm talking about that we operate. So focusing on the supply side, investment and retirement decision in supply is the responsibility and accountability of state regulators working in coordination with utility owners that own those assets. So what you have is MISO's pretty good size scale. We serve a peak load of about 130,000 megawatts annual peak load. Joe made reference to Indianapolis Power and Light earlier, but Joe and I worked for IPL in the late 90s or the late 80s, mid 90s. That was a very small power system, 3,000 megawatts peak load. We'd coordinate our little portfolio of a half dozen generators and ensuring supply and demand balance, and we'd also plan for resource adequacy on a forward-looking basis. We would run in those small balancing areas typically to ensure reliability going forward. It wasn't unusual for us to have 20% planning reserve, so our capacity installed was 120% of what we thought our near-term peak loads were. When MISO formed in 2000, we combined 60 Indianapolis Power and Light sized power system operators into a 130,000 megawatt system, combined all their operations. One of the benefits of doing that is I need much fewer planning reserves to ensure the same amount of reliability. So MISO started, we all had 120% reserves. We had a lot of reserves on a system that arguably only needed 108% reserves to ensure that same level of reliability. Here we are 25 years later, and we've been wildly successful in working that down to minimum. The MISO region hit minimum planning reserve requirements in 2022. I say that and I stress that because we're a little unique at MISO. NERC just published their updated resource adequacy reliability planning outlook just last quarter, and there were several regions in the country that were showing moderate risk of a resource adequacy reliability event in the near term. There was one region that was showing high probability. It was MISO. It's this part of the country right here. We are at minimum planning reserves. No one was talking about load center driven growth. Now, keep in mind, we've not seen load growth in this part of the country in 20 years. Well, it's not quite 20 years. At the onset of the 2008 economic crisis, we've seen zero load growth in that period of time. 12 months ago, no one was talking about load growth. Now here we are, we're talking about doubling the size of the electric system in the next 10 to 15 years. We're at minimum capacity. You can build a data center the size of half of Indianapolis in 18 months' time right now. You cannot build a supply system to serve Indianapolis in 18 months' time. You asked about DER earlier. I'm a DER fan, right? But in the Midwest, when I look at when is DER going to play a role given economics and preferences of customers, I was thinking 2035 was going to be a hot issue. That changes now with load growth because you just can't add enough traditional supply or commercially viable supply to meet this demand growth. You're going to have to get into the demand space. What was the question? I've been filibustering.
So no, I mean, you're actually starting to hit on it. So it's what do you see this tension in addressing the load growth for data centers, and what could that result in from a future standpoint that maybe wasn't being planned? So here's my slight criticism of the industry, right? We tend in this industry to think about big new things as being a problem because it's a big change, whereas a lot of other industries, like tech industries, view it as big disruption and then an opportunity to do things differently and look 10, 20 years out. So data centers have arrived. They're wanting a tremendous amount of new load. They need a lot of base load, so it helps SMRs and other things. But what does that look like in your mind in terms of what might come out on the other end for consumers?
I'll take a different view of that. So first off, at NiSource, our mission is safe, reliable, low-cost energy, clean energy for our customers. We haven't talked a ton about customer cost in the first panel or in this one. Joe mentioned it a little bit. But customer cost, huge issue in the country. And the transmission system build-out that is required, absent data centers, just aging infrastructure, is going to add customer cost. All the neat digital stuff we're talking about is going to add cost. None of that stuff is free. The way we see it, so we're a 2,400, nominally 2,400 megawatt system, and in our latest integrated resource plan, we see that more than doubling here in the short term due to data centers. But we've done two things. One, where we've built a structure to be able to do it where it doesn't hurt the customer. Yeah. And then secondly, we think that as we grow and increase revenue from the data center, we can do more things to help the customer. Overall. So we see it as a positive. Now, the tension, you know, the beauty is in Northwest Indiana, very robust electric transmission system, very robust gas pipeline system, and we also have a very readily available gas. So all of those things are positive, which I think is going to help Northwest Indiana become a mini Virginia in terms of a hub for data centers. But where the rub comes into play is land. So to build these power plants, to do the transmission that we have to do, all takes land and right-of-way that somebody owns and has to sell to us. And I think that's going to be one of the things that we're going to have to look at. And when people learn that we're going to put a power plant on that land, then they don't want to sell it to us because they don't want a power plant right next to where they are. So I think the tension is more there. I think we're going to show the customer that the data center is going to actually help them overall from a cost standpoint.
So, Bill, I applaud that, and I want to point out that NiSource, NIPSCO, was really an early mover in this idea of kind of making a decision to separate a bit how you approach and deal with, because you've had large industrial customers for a long time, how you deal with them versus the residential and commercial to realize that tension is there. And I couldn't agree more with you around helping the consumer understand why these new data centers and all the infrastructure to support them is going to benefit them in some way. And I think that you're saying that exactly. And any other comments on this one, and then I want to move on?
Yeah, no, just to resonate with your point and to validate some of the points you were making, you know, certainly we are in a time of tariff and customer rate innovation, and we are starting to see some movement in other utilities around the country, particularly those that neighbor Dominion Energy, in the direction that is really along the lines of what we've had for a number of years, and that is insulating the distribution costs associated with data centers from residential customers by instituting contract dollar minimums for infrastructure that's required to connect these large loads. So we've had that in place for a while, and it seems to have been effective. What I will say though is, on the transmission side, as we've invested in transmission infrastructure over the last decade plus, infrastructure that has been driven by data center large loads, we have seen a shifting on the transmission side of about a half a dozen percentage points of cost away from residential customers towards the data centers themselves. So the data centers are paying a larger share for the transmission costs, which are costs that...
And they should.
And they should.
Yeah.
And so, but everybody is benefiting, and that's the interesting thing about transmission. And back to your point, Bill, everybody benefits from investments in transmission. Transmission, by its very nature, is not local. It affects the bulk electric power system. And so over that same period of time, that same decade, while we've been certainly increasing our investments in the electric transmission system, we've seen nearly a four-fold reduction in transmission substation minutes out. We're now a quarter to almost a fifth of what we were a decade or so ago. What that translates into is less customer impacts due to transmission and substation issues for all of our customers, not just the large digital or data-centric loads.
So as we build out this infrastructure, both the transmission, long distribution transmission, local distribution transmission, potentially with lots more connections to distributed resources, and then we're adding in these new data center assets kind of spread across the system, which have a lot of fiber coming into them. And if AI continues to be, a major national security, kind of economic security variable, we're going to have more points of potential risk when it comes to resiliency and cybersecurity and managing these assets. So, Nick, what are your thoughts about, because you deal a lot with the operations and control, sort of how do you view the future of managing the risk of cyber and resiliency, not necessarily just cyber attacks, but cyber physical security even?
Yeah, we talk about generation planning, transmission planning, resilience. We talk a lot about, or you've heard a lot about all of the above approach. And with security, I see it, needing the exact same approach. You have your IT solutions, you have your isolation of your OT and IT networks, you have, password controls, other things to keep the intruders out. And, similar to the physical side, we've really enhanced our physical protection around our critical assets, the stronger fencing, the ballistic protection, the even access controls, improved two-way authentication. There's a number of things that we've done from a situational awareness to improve our security. But one thing at Mid-American that we will never lose focus on is just the human factor when it comes to security, and knowing that we are the weak link. We really have to train our people, we have to test our people, and we have to validate that they know what to do, when they see things that could be a potential vulnerability to our system.
As we think about security, there's another variable, and I want to maybe give Joe an opportunity to speak to this. Obviously, all of us have witnessed over the last couple of weeks the impact of the wildfires, specifically in Los Angeles, but we know that these wildfires have become commonplace on an annual basis now, year-round in many cases, in your service territory or around your service territory. And of course, we see hurricanes and other kind of weather events impacting operations of probably others here, and then even extreme cold events, which usually are the times that trigger those real challenges from a resiliency and capacity. But Joe, what's being done, and how do you see the grid system 20 years from now, recognizing that these fires may be a reality that stay with us?
Yeah, and obviously the devastation we're seeing in Southern California, but as you alluded, the fact it's not just California. When you have wildfires in Texas and what happened in Hawaii and Canada, and, oh, by the way, New Jersey. Who would have thought New Jersey? So extreme weather is here. Obviously, we're trying to find ways to decarbonize, to be able to reduce that. So we talk a lot about at PG&E, reducing the physical risk. And I would say in three different areas. There's the long-term mitigations, and I'll talk about that. There's shorter-term operational mitigations, and some of the partners in this room are helping us with that. And then there is situational awareness, and where sensor and information and AI, and I'll talk a little bit about that. So long-term mitigations, as you think about wildfire risk, we announced undergrounding 10,000 miles in our high fire threat area. People said, well, isn't that costly? But when you think about the impact that you're seeing in Southern California in terms of the impact of wildfires, for us, you think about the resiliency. So we can underground, I've got 150 radial circuits over 100 miles long. radial distribution circuits, okay? I cannot rebuild those enough to be able to provide the resiliency. So how do we think about this to where undergrounding reduces the wildfire risk by 99%? It provides greater reliability because those are going through vegetation areas where obviously tree strike potential is an issue. And then as you think about the cost situation, just to give you a number, PG&E spends about $1.5 billion a year trimming trees. That's a B, not an M, that's a B, $1 billion a year trimming trees. So when you think about the ability to mitigate the physical risk, you can do that affordably. So that's the long term. When we think about the operational measures, it's what do we do today? One of the things important, like in wildfire risk, it's for us lowering or mitigating the incident energies. So if you can trip that circuit, you know, and I think David talked, if you trip that circuit quickly, you lower the incident energies. And so there is a trade-off to say, we're going to protect our customers in our hometowns, and when something happens, we're going to trip, and we're not going to reclose. Why? Because the incident energies will go up. There is an impact on reliability, but first and foremost, we have to make sure that we can mitigate the physical risk. And I'd say one of the other areas is truly leveraging data and AI and sensors. I'll give you a great example. We have roughly 1,500 cameras throughout our 70,000 square miles of service territory in the high fire threat area. And they're trained to say, look for smoke. And they have to differentiate between smoke and fog. Why? Because being a first responder, if you see something and you can respond quickly to be able to mitigate that, either the state of California or us getting our Black Hawk helicopters out there to be able to extinguish before something happens. And so ultimately, you think about the layers of protection. And then longer term, you think about the design standards. You know, we have to be changing our design standards to take into consideration, wait a second, rising sea levels. We have substations in area around the Bay Bridge that likely are going to be underwater. We got to be thinking about the design standards to incorporate the impacts, you know, of climate change. You think about transformer standards. Who would have thought we would have 80 to 85 degrees in San Francisco? You know, the place where they said, you know, our coldest time was a summer in San Francisco. We are now having to think about air conditioning load as well as potentially 2 EVs charging in that area. So you have to incorporate that. So it's that multi-tiered approach, long-term operational measures, and really using data and information very smart and intelligently to be able to give you good situational awareness.
Hey, Joe, one thing I'd like to applaud you guys on and just mention, and you probably didn't think about talking about it, but the previous panel talked about 1 SMR versus 40 SMR and the cost. And you talked about undergrounding transmission and how expensive it is. However, you guys have done tremendous work to drive that cost down. And through driving that cost down, the rest of the industry is going to be able to underground transmission, and that cost is just going to go further and further down as we get better and better. You want to talk about that?
Yeah, and that's been the focus. We knew that someone had to be a first mover and say, but you can't just look at the cost. You have to look at all the costs associated with this. Look at the cost of Southern California right now. I mean, they're talking in the range of potentially up towards of $50 billion of impact to that, and it could be higher. You're right, and so ultimately you got to look at the total cost. And I also applaud some of the folks in this room. So, you know, David's in here right now, and one of the things I had a conversation about a year ago, and we thought about some of the operational measures to said, I need the ability to have high impedance tripping. Okay, just to understand this, we trip a distribution circuit, a 12 kV circuit, for 1 amp of primary fault current. You would think, Joe, you're crazy. What's the impact on reliability? The reality is, you know, one high impedance fault with the right wind conditions can be a 1 million acre fire that damages the structure. So one of the things we talked about is saying, we'll be the first customer okay? We will trial this. We need this to be able to, for our protection, but others will come, and you see it now in light of what's happening. So it's us, and that's what I love about this consortium. We've got the right group of utilities and our utility partners and customers to get us to the right solutions.
I want to do a time check. Are we out of time? 10 more minutes, okay. So I think I want to say something about the underground, because I was hoping it would come up. We run this other event that involves a bunch of universities coming from around the world for autonomous race cars. And every time they come to the United States from Japan and Korea and Europe, they're always pointing out, why are all these power lines, you know? So I do think it's important for people to understand that, like, the idea of burying infrastructure is not some novel concept just being done in the United States for the first time. It's just not been part of our DNA for a long time. And I do think in that 20-year outlook, as we're going through this rebuilding of infrastructure, building smarter and building more for the future versus, you know, building maybe the way that is the lowest cost and just kind of replacing things that fell over is a trend that we're starting to see. Let's talk about workforce. I know the other group spent a lot of time on workforce, so we don't need to necessarily rehash that. But I think the conversation there was more the immediate need for workforce, because they were talking about what are we going to do to get this generation built, you know, today, tomorrow, next month. What do you think is the opportunities or the challenges around workforce as you think 10, 20 years out? And how do you see the workforce of the future for a company, you know, 20 years from now? Bill, you want to take a shot at that, and then really open it up to anybody that wants to share their thoughts?
Sure, I'll start. Obviously, data analytics, machine learning, we're going to have people that understand that. But I go back to the first panel and talk about the basics. What, you know, so I'll say boiler up, Purdue grad here. What Purdue gave me was a great foundation of the basics and the standard engineering principles to go learn and do a whole bunch of things. So I'm a nuclear engineer. I run an energy company that has no nuclear plants in it. I've run nuclear plants, but I run hydro plants, fossil plants, done electric transmission as a nuclear engineer. And that's because the education that Purdue gave me allowed me to learn and grow fast and adjust to different things. Got to keep doing that. Now you can add some of the additional things that will help in the data world, which is where things are going. But that baseline science is not going to change, and people got to understand that so they can do the neat and innovative things to make our system better.
I love the basics. I mean, you think about truly understanding the basics. I think that allows you to do something else that's critically important, is you teach the field, and the linemen, journeyman linemen that are out operating the system, and you introduce this new technology. Really thoroughly understanding the basics so you can explain things well, I think, is a critical skill to build.
What about automation? How do you think, I mean, so yes, data science is super important, but the goal of a lot of this AI is that the data science is getting done through alerting-based algorithms that are pulling that information. I was in a presentation from NVIDIA dealing with autonomous vehicles, and they're showing how they took a bunch of videos of cars driving around San Francisco and then used the AI to cause the cars in that video to not behave the traffic rules. Right, so you could even, maybe mimic what would happen in a fire situation and understand how your system would react. So how much do you think the utility industry and the grid system becomes automated? And do you think, obviously there's going to be a human in the loop, and obviously there's going to be the need for people to go out and do things and touch things, but how automated do you think it could be?
I'd like to make a few remarks on that. A number of years ago, probably close to 15 years ago, we developed a system that we call the sixth man. It was I think we premiered this system. We ended up rolling this out like
I think that's
in
the
March
Purdue basketball
Madness.
team.
Yeah, in March Madness, and so yeah. Anyways, but the whole idea was we have all of this data coming in from all sorts of sources on the grid. If we could, when we had a fault on our system, if we could automatically concentrate all that data and apply some analytics to it automatically, then we could really reduce SAIDI minutes just by providing an automatic report and digest out to our field organizations. So that's actually not something new that we've been done, but something that we have improved over the last decade plus. Last year I had 3 drones in substations. Okay. This year I'm adding 15 more, and we're already coding in sockets to the sixth man to automatically dispatch those drones to the fault location, and then bring that information back, so that now I'm not only giving a location, but if there's any pictures down, if I've got a tree on a line, or if I've got a structure fire, or if I have a fire, all of that's automatically being put in. Now we don't have that. We don't have that without the human in the loop now. I do have 2 humans in the loop, but we're looking forward to that day when that's totally automated. And I'm not talking about 15 drones. I'm probably talking about 115 or 150 drones. So I think automation quite a bit. That's just one example on the operations side of the business.
Thank you.
It's here.
That's a great one. All right, we are almost done. It's 5 minutes left, so I'm gonna open it up and see if we have any questions from the audience. We probably have time for 1 or 2 questions.
So we talked a bit about workforce development and what are the needs for the engineer of the future. I wanted to think a bit about, are there any needs for lifelong learning for people working in the industry to come back to school and take online courses on machine learning, power systems engineering, optimization?
I would say absolutely, and I'd like to resonate with the comment that you made, that it's not just the engineers we need, although I need about a couple hundred of them. So I'm hoping that I'll get some clicks from Purdue IP addresses on my postings. But also, we're also engaging with career and technical schools to bring in, really those folks that are looking to get their boots on the ground right straight out of high school. Maybe they've grown up in an environment where they're handy with machines. They can come into our company as technical assistants, work their way up as an electrician, maybe then upskill to a technician, and who knows, maybe they are pulled in the direction of an engineer. We've had some people that have taken that exact path, where they started out as a craft worker as a represented IBEW, and now they're an engineer, and actually now they're they're a leader in the company. So all along the way, there's opportunities to sock it in with Purdue and other educational institutions to upskill the workforce along the way. Love the idea, and I love all modalities of it. It doesn't all have to be virtual. It doesn't all have to be at night. Some of it can be, on campus as well, or even you coming to us.
I'll say some of our best leaders and best engineers started in the field. Because that practical experience is invaluable.
Yeah.
Yeah, I'd also say, too, the ability for cross-commodity learning. As you think about the growth that we're seeing in the electric space, we're not seeing as much growth in the gas side. So being able to have learnings from, taking a gas engineer and being able to transfer over to electric engineers. So I think there's plenty of opportunities for us to be able to upscale that talent and to learn new things.
We're a gas company, man. You can't be saying there's not that much growth on the gas side.
They're just going to use it all for electricity consumption.
That's right.
Any other questions? You got maybe one more? Yep.
All right, I'm closer, I guess. You guys talked about long-term, what technology you see helping your companies. What are the things that you're working on the short term that you're really excited about, either from a technology or from a strategy perspective?
I mean, I'll give you one right now. We're actually putting devices on our poles that allows us to be, we talked about what's really important for us to be able to isolate when there is a fault and even a high impedance fault. But as Dave said, the next is how do you make sure that you can disconnect and de-energize before you actually have a spark? And so putting devices on poles that will actually be able to see where do you actually have some ingress of a tree limb that potentially could be a high impedance fault. Where could you see a situation where you actually have a lean in the pole before you actually have a failure? So to me, that's what we're actually piloting right now to give us that more situational awareness on the mass assets on the distribution side.
If I had to pick one,
your drone thing was already pretty cool.
Yeah, well, there's the drone thing. You know, the DLR space, there's a lot of talk about GETs, grid enhancing technologies. The types of load growth we're seeing in our service territory is a capacity expansion problem first and then an optimization problem. It's not an optimization problem and then a capacity problem. And I think we kind of get that reversed. But that said, there's a lot of promise in terms of the operational flexibility that GETs can provide. And so we're in a, if it continues to be funded, we've just started a DOE project where we're going to deploy the largest DLR project in now. Some say the world. I can at least attest to the country on over actually nearly 3 dozen transmission lines getting DLR technology installed. Really excited about seeing that go up, not only just for letting us understand capacity, but also some of these security issues and wildfire-related issues, learning what other data can we pull in from this technology stack that can help us operate much more flexibly into the future, and then also help us on the optimization and the capacity side.
Just to add on to that, in the control room operating environment, we've added a lot of technology and optimization solutions into the control room over the last 20 years. But if you look at the role of a power system operator, the concept of operations for the power system operator has really not changed that much over the last 30 years that I've been paying attention. We still have our operators that are tightly integrated into control room processes where they are integrated to make decisions in support of reliable power system operations. It makes sense. As we move into a future with a very different looking generation system, a transformed power system, the implications of that are much more dynamics on the transmission system. We talked about more dynamic distribution systems earlier. That points to the need to use advanced analytics and leverage data, bring in robotics and automation to help automate some of the roles that operators play today. Compare this to the airline industry. My neighbor is a FedEx pilot. I asked him about flying planes. He says, I don't fly planes, I fly simulators. I ride in my planes. They fly themselves. He's there to interface if he needs to, but he flies simulators. The current state of simulation in the power system control room environment, it's far from a rich simulation environment. We need to move to a world where our operators are being trained in operating simulators, and we use automation to make more complex decisions, or at least make decisions in a more complex operating environment going forward. We've done some of that at MISO. Historically, operating reserves, the amount of surplus reserves you carry to handle uncertainties in the operating time environment was pretty static. You'd do studies over 3 years, and you'd say, roughly, I need 100 megawatts of regulation. You had 100 megawatts of regulation service every day of the year. Now, the need for operating reserves is dynamic. Days look differently. If I have a high wind forecast versus a low wind forecast, it changes my risk profile. So we brought in some partners to help us run and build machine learning models. So now we're setting our reserve requirements dynamically day to day based on the operating risk profile we assess for that day. So that's a small example of how we're trying to change the historical approach to at least operational planning in the control room.
I think to keep us on track. Do you have time for Jay? Okay.
One,
go for it, Jay.
I'll ask it very quickly. All of you mentioned the value of big data. One of our experiences working with 10 years worth of data from a utility plant that I would not mention here publicly was that bad data are the enemy of the biggest data that one could ever find. And one of our tasks became separating bad data from good data. My question is, are you all planning, as you are planning to accept big data and machine learning and artificial intelligence, are you also planning how to segregate bad data from big data?
Yeah, maybe I'll start. 2 weeks ago, the senior leadership team of PG&E went off-site, and one of the topics that we had for the two-day session was around data and data quality. And I will tell you, it's something, we have a robust data set, both on the gas side and the electric side. How do we continue making that data set better? How do we continue having a better understanding of the asset health and the asset registry of that data, such that when we actually start doing that modeling, and we're doing a lot of that today. I would say on the wildfire side, we have this incredible accurate data set that we're leveraging. As we continue, how do we do that on the mass asset side? When you think about 3.2 million poles, how do I make sure that I have good asset health on the distribution system? I have it in the substation, but how do we continue to deploy information and data and sensors to give me that true data? And then how do we cleanse it to make sure that we can get the right outcomes?
I just want to make a comment here on this topic. I think this actually could be an area where Purdue could really excel. The reality is this big data challenge is going to cut across industries, right? If we already know that Tesla's cars are driving all around and they're gathering all the same data that a lot of your cameras are gathering, and they can see if something's happening, or your camera can see if something's happening and let the car know that that's happening. So I think if we go out far enough, that ability to do big data management and then layer in foundational AI models, which can do all the labeling for you and can segment the data into what's actually useful for training, is definitely doable. One of the big challenges is going to be privacy and who owns that data, and how do you actually aggregate it and work with it. But universities and campuses are a great test bed for that kind of work.
I would just say this one thing. In the interim, until we get there, which I do think that is sooner than later maybe, we celebrate bad data. And what I mean by that is I had a meeting with some of our engineers in our operations center a number of years ago. We'd spent a lot of money on deploying synchrophasers. And they said, oh my goodness, Matt, something's wrong. You got to come look at this. And they pulled me in a room and said, look, it's all bad data. And it was like 70% bad data or just mischaracterized, mislabeled data. It was a mess. It was absolutely a mess. But I said, this is a moment to celebrate. We should pop a bottle of champagne over this, because you're complaining about that, because you're looking at the data. And that's rule zero of getting value out of data, is to look at it and to get that sense of frustration that this is bad, because you're frustrated. You're frustrated because there's value that you want to unlock that is frozen behind, bad, whatever bad data hygiene is causing it. Well, now you're going to go get it. So in the interim, we celebrate bad data.
All right. Well, thank you all. This has been a great panel, a great conversation, and thanks to all the panelists. And I think we've got a break here for a little bit, and then we've got another one of these that's going to be exciting with a focus on AI. Great.
The day, and I'm really delighted that our moderator for this last session on the nexus of AI and the grid is Patty Poppe, CEO of Pacific Gas and Electric, and really happy also that Pacific Gas and Electric has been such a great partner with Purdue University in getting us going on this Grid of Tomorrow consortium. So without further ado, over to you, Patty.
Oh, thank you, Dean. Well, hello, Boiler Up. Boiler Up. Hello, good to be with you all today. And I really am excited about the potential that today foretells. I think, as I was sharing with the Dean, look, Purdue's power engineering program is legendary. Purdue's industrial engineering school is legendary, if I might say so myself. And I think, yeah, that's right. And all of the research that's happening here around energy and data and how all of the optimization comes together is so important right now for America's grid. And so I can't think of a better place than Purdue to have this conversation and have many conversations yet to come. So with that, let me introduce my panelists. we have the best of the best with us. We're joined by Mark Spieler from NVIDIA, the Senior Manager of Global Energy. If you haven't heard about NVIDIA in the news every day for the last 2 years, I call it the overnight 30-year in the making sensation. NVIDIA is incredible, and we're so proud to be, at PG&E, we get to serve NVIDIA. It makes us very proud. And I'm joined with Louis DaCosta, who is from Schneider Electric. He's the CEO of Uplight and Senior Vice President, or EVP at Schneider Electric. AJ Booth from Tesla is the Senior Director of Products and Engineering, another favored customer of ours. We serve Tesla in all forms, and we in fact, we rank all of our partnerships. And 2 of our very top partnerships are Schneider Electric and Tesla, because this is the future of energy, and we're so proud to be working so closely with both of them, both of those companies. And then Raza Kaj from Plug and Play is a very important venture firm based out of Silicon Valley, one of the smartest places I've ever visited. When you find out about the business model of these guys, they house all the startups, figure out which ones are good, invest in them, and they've launched how many unicorns?
32 officially, and many gonna be announced this year, at least 4 or 5 more.
It's incredible. It's incredible. You want to see the future, go see these guys. And I understand, well, we'll talk about what you're doing here at Purdue. I don't want to steal my own thunder. Okay, so again, the intersection of AI, the power of data to optimize our grid and deliver high quality, safe, reliable electricity at a time when America will need more electricity than ever before is just a perfect intersection. And so we're excited to talk about all those things. I think I was supposed to have them introduce themselves, actually. So what I am going to do is allow you to, you can say your name and your location or your company, but tell us a little bit about what you think the future of the grid holds for your company. So why don't we start, AJ, with you?
Really, our mission at Tesla is to accelerate the world's transition to sustainable energy. So like the Grid of Tomorrow is that is really our mission, which is why I'm excited to be here. And so like we're looking at, from an acceleration perspective, what are the things that aren't moving fast enough that's really preventing the grid from going fully renewable, and how can we help in that? So I mean, that's why we started with energy storage. So we've deployed a lot of energy storage. There's a lot of use cases that have been really great and I think accelerating. New loads being applied, like data centers and things, and as we look for renewable energy and like how to use power electronics to really accelerate, adding more generation and supporting loads, and using the assets that are already deployed to the grid, like home batteries. There's a lot of EVs, which are mobile energy storage on wheels. They have 11 kilowatts or more of power connected to them, and like figuring out how we can use all of those things so that we can really build the grid that we want that's renewable as quickly as we can, because it really does matter how quickly we do it.
That's right. Well, and I'll just add, AJ's underselling the importance of the home battery systems. I'm very bullish on EVs, so I can't wait for those to be bidirectional. But the fact is today, in our service area, we can dispatch our Tesla home batteries all across our service area and are able to deploy that energy to the grid. And we do that on peak days. And so we take existing assets that people, I call it anyways economics. They bought them anyways for their own home resilience, but then it can serve a very low cost value to the grid. Then you get the multiple value stack of home storage. It's just been wonderful. And Tesla so quickly moved. We had this idea, like we've got a hot summer coming up, and in 2 weeks, they deployed the capabilities of the app. I mean, it felt like 2 weeks to us. Maybe it was longer than that.
It felt longer, but it probably was 2 weeks.
And so in 2 weeks, we have this new app that's on the phone that Tesla Powerwall owners can automatically dispatch their power. It's seamless, it's easy, and it's just scratching the surface of what's possible. Why don't we go to you, Louis?
So Schneider Electric, very, very focused on sustainability, one of the most sustainable companies in the world. And we are really focused in this mission on how do we connect much more focused on distribution. How do we connect, let's say, the living room with the control room? So a lot of what's very exciting for us in the partnership with PG&E in particular is this idea of one DERMS. How do we harness not only the integration of the different data streams to improve the operation of the grid, but also how do we harness other people's assets in order to put them at the service of all grid stakeholders. So each of these electronic devices that are behind the meter are a sensor in themselves, right? All of them have the opportunity to be dispatched and create this great value at a low cost. And I cannot think how we can have a grid of tomorrow without really taking advantage of other people's assets when we are planning the future. So that's what we are doing these days, and very, very excited with the partnership on PG&E for this.
Well, okay, I have one more story I got to tell, and it's actually about these two guys. So some time back, Tesla came to us and wanted to power a 3.8 megawatt supercharger. And Joe's distribution engineers, I'm going to blame your engineers. We love those guys. But they came back and they told Tesla that we'll be able to get you that power in 4 years. So as you can imagine, Tesla is not our most patient customer, I will say. My phone started ringing. What are you talking about, 4 years? But here was the challenge for our distribution engineers. They are required to engineer for the peak day plus an 18 to 22% reserve margin. So on that circuit, there were certain days of the year where we could not serve 3.8 megawatts, so it was never. If I can't serve peak plus reserve margin, I can't ever serve you. Well, thanks to Schneider, we were able to develop what we call our distributed energy resource management system with what we call reconnect. When we went and calculated the by-hour loading of that circuit, there were only 20 hours in the year that we could not serve 3.8 megawatts. So as you can imagine, Tesla was okay with that. You can have the power now. You can have the power now. But 20 hours of the year, we need to be able to curtail you, and we have to be able to control that. Because if you're the distribution operations center, the last thing you want is to count on Tesla to turn off their own power on a peak day. We love you guys, but we don't trust you that much. And so we have to be able to control that. And so our control rooms need that confidence. And so designed in through our Schneider Electric Distributed Energy Resource Management System, we can, in fact, control that load. And they can then send signals to their drivers to say, go around that supercharger and go to the next one. That is a modern, optimized energy system. Imagine if I only served them by building 3.8 megawatts more of generation, 3.8 megawatts more of substation capacity, 3.8 megawatts more of poles and transformers. What a waste, when in fact I didn't need. Now, in time, when I'm upgrading that substation and that circuit for all sorts of other growing load, we can optimize what we build all at once and serve that 3.8, 365. I just think it's such a perfect example of how the future is just starting to unfold. And literally, we have 7 customers on that flex load. That we should have 7,000 customers on that flex load ultimately. And so we'll build out all that capability. So thank you, guys. Raza, why don't you say a little bit more about what Plug and Play is up to and what you're up to in the world of AI and energy?
Absolutely. So my name is Reza Kaj, part of the Plug and Play team. We are based in Silicon Valley, but we are all around the globe, 60 different offices, 5 continents, and we work with 500 plus large corporations around the world. We connect the brightest minds, the best startups with the most innovative corporations in the world. And within the energy industry, we are working with all the utilities, oil and gas companies, EPCs, that they're trying to kind of moving towards a more greener and sustainable energy solution. On that front, I'm leading the energy vertical there, but kind of like on Plug and Play sides, we have 3 sides of business. One side is the investment that you mentioned, and we have been very fortunate with the investments that we have. But the other exciting part that we are partnering with PG&E is the corporate innovation. We are kind of an extension to their innovation and R&D department. What we do, we source the startups that could potentially solve some of the challenges that we discussed in the morning, from distributed energy resources management all the way to wildfire that we mentioned, and also making a resilient and reliable grid. Yeah.
That's awesome, and we love partnering with you. And have we announced our San Jose project? Or?
Yes.
Okay, so I
Yeah.
can talk about that?
Yeah, of
okay.
course.
Sometimes I break the news accidentally and I get in trouble for that.
Yeah.
You know, we're so excited. We've got a special project happening in San Jose. We've got a net zero community that we're developing, 8 blocks with the city of San Jose. We announced a major project at our Innovation Summit where we're going to have 3 data centers in a new housing area with 4,500 new housing units in a high-rise, all electric, and the data centers, we're going to actually capture the heat from the data centers and use it as a peak offset for, and actually a daily baseload offset for all new electric residential dwellings. And we're working on building that out in a net zero way. And Plug and Play is going to have a location with us in that 8-block area.
Absolutely. Our goal is to find the best AI companies that can work with companies like PG&E and our partners in San Jose, and also growing that practice. We launched a similar practice 7 years ago in Stuttgart in Germany with Mercedes-Benz and University of Stuttgart. Through that program, we help startups having close to 400 pilot projects, and at least 6 to 7 of those projects we know like they have gone into production. And our hope is with the partnership with PG&E in San Jose, we're gonna achieve those number of pilot projects and pilots that's gonna be impactful and be applied in the services of PG&E.
Yeah, that's going to be very exciting for us. And so, Mark, another very important customer for us, NVIDIA. Mark, you know, I think a lot of people, I personally think what's happening in AI, it will be one of the most exciting things that happens in any of our lifetimes. And I'm not going to miss it like I missed the internet. You know, I was a little slow to adopt, apparently. I missed out on all the smart investments on the internet. But NVIDIA is obviously at the heart of powering data centers and all of the chip advancements that you've had, AI for energy, but then energy for AI. It's just a symbiotic relationship. So I'd love to hear your thoughts on what's happening at NVIDIA.
Fantastic. Thank you for having me. So my name is Mark Spieler, and I run the global energy business at NVIDIA. And that's not necessarily buying energy for NVIDIA, but it's how do we go to market to help energy companies and the energy industry solve some of the largest problems using our technology. You mentioned chips. Most people think of us as a chip company. And we do make GPUs, and we do make CPUs and DPUs and all the different silicon. We actually engineer them. We actually are fabless. So I was very impressed with all the nanotech technology that we saw this morning. But really, we're an accelerated computing platform company. And what that means is we develop some of the leading software platforms for solving problems in the areas of visualization, high-performance computing, and AI. And this stems back to 30 years ago when Jensen started the company and has continued to develop this. And now our latest GPUs have 20,000 plus cores. But the silicon's really good, but it's the software stack that make that significant impact. And so if you're not familiar with our software stack, that's where really the value add is. And that's why our chips get better with time. They become more energy efficient. And we're able to lead this AI revolution is because we're the only AI company that works with every other AI company. So you'll see our name with, you know, Microsoft and Anthropic and even DeepSeek this last week and everybody else, right? Because they're leveraging our platforms to solve problems that weren't commercially viable just a few years ago, right? AI's been around a long time, but it didn't become mainstream until it became commercially viable. And now, if you think about AI and AI factories, right, it's the next industrial revolution. Take your product, electrons, add data, and out comes tokens or knowledge. right? And so this is how we're going to help the future workforce to be more advanced in the way that they work and to be able to solve more problems. I think it's very clear there's more problems than people to solve, and therefore we need to augment them with access to knowledge that they couldn't get in their lifetime. They can't get in 4 years at an education, and there's so much data and so much research that's been done in these fields, but to be able to put it in front of them, it's kind of like a calculator, right? It didn't get rid of mathematicians, it just helped them do much harder math much faster, and that's what AI is going to do.
That's a great analogy, too. I often say it's like Lotus 1, 2, 3. You know, it was shocking when it happened, where I thought, what are we going to do with this spreadsheet thing? Why? I don't need it. And then figured out you need it for a lot of stuff. And so, obviously, data centers take a lot of energy, and NVIDIA still has strong sustainability objectives. How do you balance both of those things?
So once again, from a silicon perspective, every generation of GPU that we have, although it will increase in power per chip or power per GPU, the amount of work that you can do with that GPU grows exponentially. So even when we've gone from our Ampere chip to our Hopper chip and soon to be our Blackwell chip, yes, the power probably goes up by 20% per generation, but the amount of work, the amount of tokens, the amount of HPC, the amount of work that's been done has gone anywhere from 4 to 20x, right? And so once again, you're able to do much more work in a much smaller power envelope. And we're committed to the highest performance per watt that we can deliver generation over generation. But it's not just in the silicon, it's the software stacks as well. That way, even after you buy a system that's accelerated, we'll continue to give you updated libraries and updated things. It's kind of like a Tesla, right? The best day for that car is not the day you bought it, but every time you get a new software update, something's better. Same with NVIDIA. The software continues to make it more efficient.
That's awesome. Thank you. And so, Reza, as you're looking at all sorts of new startups, and you have such a great lens on innovation and the entire ecosystem, how are energy technologies showing up in your universe? Where are you seeing them, and what are you hearing from them?
Sure. So in general, in terms of investment in venture capital money that was invested in climate tech, we have had a decline since 22, but it was a minor decline last year. But two of the energy areas that was exciting, that like tripled and doubled in amount of investment, one of them was nuclear, which it was mentioned all day round today, and the other one was geothermal, which was not mentioned and also has a lot of potentials. So for that, there are a couple of unique things about like nuclear and geothermal, especially supporting AI, because they are among the clean renewable energies that can provide the base load, unlike like wind and solar energies that requires like battery systems to complement them, and they may not be always available. So we are very interested in nuclear and geothermal energies in terms of startups that we are looking. But besides that, the whole value chain of like operating a data center, it goes beyond energy providing the direct energy, but it's also optimizing the energy usage. So there are many AI startups that are innovating in managing the energy resources and managing the cooling systems within the data centers. One example, Phaidra AI, they came out of Google. They also proved a case with Google, their DeepMind team, that they could save 40% on the energy by just applying reinforcement learning into managing the energy system of data center. Then we get to other opportunities within data centers. Cooling system, I think it came up at some point in one of the panels. Like we are seeing a lot of great liquid cooling, submerged cooling that are more efficient, more sustainable, less need for large bodies of water, and so on. Then at the chip level, NVIDIA is innovating when you are able to perform more computation at a lower power that's also adding efficiency. And we heard about the news of DeepSeek this week. So other startups are also innovating at the algorithm space. So they are making more efficient models that are lighter, that can provide similar functionality at a lower energy consumption. So we are looking at the whole value chain of AI and data centers, and we make bets based on what's differentiating those startups with the comparing startups in that space.
That's awesome, and we can't wait to see who you bring to us. And so, Louis, you and I go way back, and Uplight, obviously you're CEO of Uplight, as well as Schneider generally. Help us understand the role that you see in optimization and load management. You and I love this topic. As a Purdue industrial engineer, I want to make the grid more efficient. Tell us how you see it, Louis.
So we see it in two ways. The first one is very closely coupled with the hyperscalers, the data center providers. How do we provide architectures that can provide that flexibility, that can actually contribute back to the grid and have a win-win opportunity? So there's a lot of work that we are having with hyperscalers and others in order to bring forward those flexibility, more flexible architectures, and the power system inside the data center, so DC systems, other cooling technologies. So what's interesting for me is when I meet with utility executives, they only want to talk to about data centers. When I go and talk with data center people, they only want to talk about what's happening in the utility space, time to power, and how are we going to grow. And so I think we have the opportunity to play in both areas. Now, the level of the opportunity that we have to really harness the power of other people's assets, right? And understanding the amount of devices that are connected to the distribution grid today, and we could observe and we could use and put at the service of the grid is immense. And we are using AI and technology that helps us not only predict or forecast weather, but also forecast behavioral and propensity models about what people will actually do. How do we target people in order to engage with them and help them on their electrification journey, but also help them participate in the grid? So there is a lot of, obviously we have a lot of data from the power system too, but there is a lot of data that we need to crunch. Something that is critically important, I think, is that not a single vendor or technology provider will be able to do it all. So partnering and making sure that you have the right forecasting models for different applications, that we have the right input from different vendors into our solutions, it's critical. A great example connected to the wildfire mitigation is, and with SEL and a little bit of everything, is we are getting data feeds from ESRI that helps us identify polygons, right, geographic polygons on fire risk. We overlay that with our ADMS, our GIS system, in order to, through SCADA, send to recloser controls to disable reclosing in case of high fire risk conditions. So integrating the best of the capabilities that are out there, it's critical for us to actually move the technology or move our value forward.
You know, Louis, I sometimes think of the grid like I-80, you know, just running maybe through Iowa. That I can't tell this joke in California, but I can tell it here. But you know, you're running through. It's a big long highway, and you have a couple on ramps, a couple off ramps. You got some big power plants bringing big energy on the transmission bulk system, delivering it, you know, and you might get to a town. But the grid of really today in our service area it looks a lot more like San Francisco. Like it has multimodal transportation. It's got all levels, small from the rented scooter to the big bulk power. We've got both, like we have the whole range. And thinking that we can use our old utility distribution control system to control that is not possible.
So for us, the analogy we use internally is we have spent a lot of time in our industry on improving reading glasses technology for very low lit environments, right? So it's instead of just shining more light to the room and bringing more data and more collaboration across the across the ecosystem. So that is what we are really trying to work together.
That's great. And so, AJ, tell us about how you see Tesla and the role of storage generally, mobile, stationary. How does storage play into managing this large load demand coming on the system?
Yeah, there's a lot of different ways. I mean, you mentioned FlexConnect, which I think is a great program, especially for data centers, and you can pair that with storage so that they don't actually have to deal with going down. You can add storage for 1% of the data center cost, and you get a 4-hour battery that is a 20-year asset, which is great. We've also seen some utilities in other countries use storage as a flexible virtual transmission line asset, so you can keep your N-1 redundancy, but you can uprate your existing infrastructure by intelligently placing batteries onto the grid. So you can actually get more out of the things that are already there, which will allow you to add more load. And then, yeah, just in general, hopefully, like we see homes, somebody mentioned in San Francisco, I think Joe mentioned, we get like more load even in homes, but like having generation, having local storage, having that, doing VPPs like we're doing and having that grow and be more of a standard product that customers have, allows them to add and electrify more, allows the loads can also be more intelligent, as you pointed out, including using vehicles as an asset so that we don't stress the distribution network, but we're still growing like energy consumption because we've electrified everything. And I think that's possible without, with at least delaying a lot of the infrastructure improvements if we're smart about where we deploy these very versatile assets.
Yeah, a lot of people think about this large load from data centers as being an automatic need for new bulk generation. That is not true in all service areas. I say there's like a Goldilocks of new large load. We call it net beneficial at PG&E, large load. So when a data center wants to locate in our service area, because of our high penetration of renewables, our grid is actually utilized about 45%. But because of this mindset that we have to design everything for the peak plus reserve margin, we're talking about redesigning the whole system for 20 hours a year. That doesn't make sense. So we can actually be very fast to bring on new power. We weren't before, I know. My customers let me know we weren't, but we are now. We're getting our wits about us, but we're figuring out that we can bring on new large load and just serve this peak problem. That we have at least 5, maybe 10 gigawatts of capacity that we can leverage that's available right now, as long as we can serve the peak. And we can serve the peak with all of these smart technologies because we all understand the peak is driven by residential air conditioning. It's not driven by base load, it's driven by residential air conditioning. So if you manage residential air conditioning with batteries, with smart thermostats, you manage a big part of the peak. Now you've got a whole different speed to power, which is the big question and the big need. Now there comes a point where you do need to add generation, and in some parts of the nation, their system is already close to peak. But in a lot of parts of our service area, we have ample capacity. We just have to deploy it and have a smart distributed energy resource management system that can manage the peak. That's a new generation of delivering power and speed to power at a time when America needs it most. Should we take some questions from the audience? I have more, but I'd love to. I'm sure all of you have great questions you'd like to ask. We'll start here, and then we'll come over here.
The panel that we just had before talked about the issues of data and big data, and it seems like the grid is really a great use case for how to manage big data. And I know I'm familiar with the autonomous vehicle industry, and obviously we have representatives here from Tesla and NVIDIA, and it's a lot of work being done in how you capture terabytes and terabytes of data from vehicles that are operating and then use foundational models to do a lot of the labeling and the things that would normally take a lot of time, and then to test edge cases, right? And the grid has edge cases, right? Whether that's an outage or a fire or other things. Do you see a scenario where the kind of tech industry and AI can be partnering more effectively with the grid sector to develop these kinds of simulations and test case scenarios? And given maybe the universality of some of those challenges, and not necessarily that it's a competitive advantage, maybe it's something that could be pooled across markets.
I can start. I think our industry has suffered a little bit about customer engagement and this idea about it's my customer or your customer. So we all understand that there is issues with data privacy and data security and everything else. However, we have been extra private in our industry, and it's being more difficult to share. Now, we do see that changing these days, right? So, as an example, with the Pacific Northwest, we have a large VPP that is multi-asset, right? So, and we are forced, because of regulation constraint, to continue to do old MMV metering and verification processes that are statistical, that are from a time where you didn't have reliable metering. Instead of me calling Tesla and say, hey, please send me the data about the charge and discharge profile of the assets that are in the pool. And I can get that in near real time with a level of, let's say, precision that simply you cannot do in 15-minute interval load profile metering data that is what we have been used to do in the past. So I think the collaboration is starting to happen more and understanding the limitations of data privacy, and we are trying to share, anonymize, make these pools more available. A lot of the grid data is already available to all of us. Huh? So it's just a matter of that. How do we really, I think, bring it together and share in an orderly fashion?
Yeah, and create value from it.
I'll give you a couple of examples of how we're working across the industry to do this. I think your point about autonomous cars are really important, right? When you first start training autonomous cars, you've got a trunk full of hard drives. You go out and collect a bunch of data. You start building models, and then you push those models out to the edge, and you see how good they are, and you collect more data, and you continue to evolve, and then eventually you have millions of cars, and you're collecting lots of anomalies of what's not in your model, and you retrain. We're doing that today at the edge. So we've released a grid edge chip that for the industry, we're working with 4 companies right now, Duquesne Light, Portland General Electric, Consumers, and ComEd, 4 very different use cases to basically put 170,000 of these units across their grids and basically capture data, train models, and then we can push the models out as we continue to train. But those models will be available. They're going to be open models. They'll be available to the industry. And so we're doing that today just like we did in the auto industry with, Drive and Drive Sim and all of these. Because ultimately, what we find is that everybody experiences different situations, right? Living in Texas, we didn't expect the cold snap we had, but if we could have got data from Minneapolis, we probably could have saw some of these things before they happened. The second one is we're working very closely with EPRI, and the work that we're doing with EPRI right now is to, we'll make some formal announcements, but we're building a consortium there specifically around building a power industry-specific LLM, training it on all the EPRI data, building out tools, working with, I think there's about 10 companies, I think you guys are one of them, to train a model that we can then open to the industry and allow them to continue to build on it, leverage federated learning, and basically allow the entire industry to start with the understanding that you can't get from a traditional open source model today that's just too broad, right? As small as model as possible, right? Maybe it's 30 billion parameters, 70 billion parameters, but it knows everything about the industry. And this is where we talked about the future workforce. The future workforce will be prompt engineers, right? And they will be able to look at these models and answer the questions, are they accurate or not? They're gonna do Q&As, they're gonna create prompts, and eventually you'll have a power systems engineer, and you'll have a field operations engineer, and you'll have all these. And so when new people come to the field and they're starting to work on equipment, they could take a picture and say, what is this? And they'll say, oh, it's a Schneider XYZ, and, you know, what do you think's wrong with it? This is what I see. And they'll say, well, you know, based on other, you know, root cause analysis, it's this. Well, do we have any in stock? Or where's the closest one I can get? Oh, actually, yep, 30 miles down the road, we have some of those in inventory. Okay.
And just to, this is not sci-fi or things that are 20 years from now. So we are piloting things with PG&E and others using Google Lens and virtual reality or augmented reality things in order to diagnose equipment today. That's technology available today. The last thing that I would say is that it's happening in our industry and it's happening very fast. So only 18 months ago, the VPPs that we had where you push a button and you hope for the best. How many people will show up? It was always now we can forecast and nominate megawatts with very, very high precision. So being able to use these models to making virtual power plants truly a reliable resource, right? Something that you can expect, not just hope for.
Yeah, I know we have people from MISO here, and I know as a system operator, demand response in its traditional form was not reliable because it was just big interruptible contracts with large industrial customers who, in the heat of the moment, they might follow their contract on the first day, but come the second day, they're not going to stay down for production. And so they'll pay through, which is not a reliable form of demand management. But the tools and techniques that we're talking about here make that kind of capability, like our VPP with the power walls, those are reliable. You can count on them. And it doesn't require 100% participation. You know you have a opt-out rate within your user population. It's very feasible. And then the ideas of a large language model for the entire industry and the ability to more quickly learn lessons from one another, especially in our sector where we do share quite openly lessons learned with one another, and we know that the grid is a system. No matter how you slice it, it's all connected. And so it's in our best interest to serve and learn it together as quickly as possible. It's so amazing what's possible there. Here.
Thank you for taking my question. And I want to sort of mention that the discussions you have related to big data and all of the VPPs and so forth, virtual power plants, I'm going to introduce that phrase tomorrow in my thermodynamics class. But in yesterday's class, we did discuss heat pumps versus refrigerators and coefficient of performance for one being higher than the other. And my question is, are you encouraging your customers to move from refrigerators to heat pumps or air conditioning to heat pump? Because there's 25 to 30% capacity hidden in that efficiency gain that they will benefit from and you will benefit from.
Yeah, we are, and we incentivize our customers to do so. It is going to be a critical element of that San Jose project I talked about, one of the first major cities at scale to attempt a full net zero in an 8-block urban area. Heat pumps are going to be essential. That'll be an essential ingredient to going electric. And so I think, and having smart heat pumps is like the holy grail. So we definitely see that that's a huge opportunity to address this peak, summer peak problem. Yeah.
Great deal of work at Purdue in that area, actually.
Okay, good to know.
In our Herrick Laboratories, colleagues work in high coefficient of performance heat pumps with alternate refrigerants, environmentally friendly refrigerants, and so on and so forth.
Okay, good to know. Okay. Here. Yeah, sure.
I'm interested, I guess from all the panel's comments, the Tesla example where you wanted to put 4 megawatts on the line, but for 20 hours out of the year you could. That falls under kind of the duh, right? When you sit back and you look at it, well, that's
Well,
of course.
100-year duh, but okay.
Yeah, but
yeah.
and especially since you get to control it and turn it off. And then I think you said, on average, you use about 40% of your power system. So adding load kind of makes sense because you've got this 60% capacity. But we got a lot of smart people that do statistics and everything, right? To probably come up with this answer about how much you can load up. But at the end of the day, there's going to be some times, right, where the statistics are just going to bear out where you're not going to have enough capacity. And how do you manage those particular situations? I'll watch the California news, I bet, this summer, and the governor's going to come on saying, please don't charge your cars. And we might have to have rolling blackouts. And since you guys are a public utility, right, a public service utility, how do you manage how much you can actually load on and how much reserves you really need to carry for those, statistical oddities at the 3 or 4 or 5 sigma out there that are going to happen that will impact elderly people and all those kind of social type of challenges?
Yeah, look, we are not interested in taking a bet on the safety and well-being of our customers and the citizens that we serve. But I will point out that last year, and sometimes a problem that doesn't happen doesn't get noticed as much as the problem that does. And so the problem that did not happen last year in California, the 8 hottest days on record, we had no flex alerts and no outages as a result, because we've added 12 gigawatts of battery storage to the grid in California. 12 gigawatts, that complements that existing solar, where 20% of our customers have rooftop solar. That's what's creating this capacity availability. Now we can serve peak in a much more dynamic way. And we don't just have to build base load power plants. We need to build a smarter grid to serve and have the complete 100% confidence of being able to serve. And then you design your critical loads appropriately. You design your critical loads with the necessary switching and backup and rerouting capability so that we can deliver for customers. And so there's no doubt that I'm not living in a land of compromise. We're going to live in a land that uses technology to provide better service than we've ever had at a lower cost. And this is the great mystery to unlock, I think, and the great misnomer to unlock. The idea that a cleaner, more dynamic digital grid is going to be more expensive. We show we can reduce our carbon footprint by 70%, and household energy spend can go down 20 to 30%. Household energy spend can go down with a cleaner energy system. A big part of that is the transportation. So we love our EVs in California, and I know in lots of parts of the country, so here I sit in Indiana today, it may be hard to imagine, but in Santa Clara County, last year, 43% of all new vehicles sold were electric. 43% of all new vehicles sold were electric in a real county in America. So I know there's a lot of thought that maybe EVs are just a passing fancy or they're too hard to deal with. They're not. We are living a postcard from the future. We can show how those EVs can provide the dynamic power load, first time ever, electricity that you can tell when to turn on. Up until now, the air conditioners came on when it was hot, the lights came on when it was dark, the motors ran when the factory starts. Today, EVs provide the first absolutely dynamic load that with the right signals will charge at the right time and can utilize the grid and lower the unit cost of electricity. Never mind the fact that electric motors are more efficient than internal combustion engines. So the combination is a windfall for the U.S. economy if we can, in fact, embrace the clean energy transition and do it in a smart way, which is, I think, what's so exciting. So other questions? Any other questions from the audience? So Reza, how about startups and collaboration? Say a little bit more about how startups experience the plug-and-play ecosystem, and then how you connect that with real-world problems.
Sure. So maybe I add university to the mix as well.
Oh, yes,
research
please. Good.
Since we are in Purdue. So looking at deep tech and energy-focused startup companies is usually comes out of technologies that have been in R&D process for a long time, and they have invested a huge amount of capital to bring them to actual business model. So what's exciting about universities and research institutes is that you have the capital of talent, you have the research infrastructure, you have access to NSF, governmental funding, and you have time. So you can build those IPs. Then it comes to the part that how can we transfer that IP to some meaningful business? That's where I think some of the universities lack, and that's where kind of like these private partnerships or like plug and play comes into place. So there is a phrase in VC community where we call it Valley of Death, which means like how you can take a product that was developed at lab scale into a larger scale, which is a pilot with a potential first adopter or like somebody like PG&E to partner. That's where you need like these private partnerships, companies like PG&E to be that early adopter, coming in, willing to try your technology, and then proving your concept and showcasing the success of your project to other utility companies and bringing more clients. So what we do by partnering with like 500 plus large corporations is that we find, first of all, we have a great line of communication with the corporation. So we have a good understanding of like what their problem and challenges are. Then through this sourcing process that we have, we look at 15 to 20,000 startup companies each year. We try to handpick and select the top 10, top 20 startups that are addressing a real need or challenge. We bring them to companies like PG&E. They present, showcase their solution, and they get into a pilot project. And that helps them moving the lab scale project into a project that can be eventually become a actual business model. And they get a lot of industry feedback, obviously, from them.
And that's key to the partnership, because you bring those industrial customers and partners to the table to share what their biggest problems are. And in fact, we at PG&E published last year, and we updated it again this year, our top 70 problem statements in our pathway from today to the future energy system. And we wanted to make it real for innovators, because sometimes, I must admit, I get a lot of calls of people who have the next big idea. And yes, it's an interesting idea. And yes, it's actually a problem to be solved. It's just not one of my top problems. And so, you know, we waste a lot of time, you know, sifting through, trying to find the person who's solving the problem that we have. And so plug and play is a great example, and Purdue is a great example of being able to see, here's our top 70 problems. We need to solve these. If you can solve one of those, definitely call us because we need you. And so we're trying to actually create a better funnel so that you don't waste your time, and we certainly don't have excess time to waste. But, you know, we've talked a lot about the energy system, and obviously this is another key strength of Purdue in national security and cybersecurity research. AJ, I know you have thoughts about how cybersecurity fits into the ecosystem.
Yeah, it was touched on earlier. I mean, cybersecurity is vitally important, and everybody needs to do all of the table stakes, like cybersecurity measurements, to like make sure that your assets are as protected as possible. You know, at Tesla Energy, we sort of had the benefit of being young, so we're 10 years old, so we grew up in the digital age. So like all of our assets, all of our data is already like in the cloud. We have all the information. We scrape it. We have like auto tickets generated for our service team. That's why we're able to do over 99% availability at our supercharger fleet at a global level. And like, so like building up that infrastructure and then like maintaining it and preventing intruders is super important. And one thing I heard today, actually, when we were at the nuclear tour, was that you know, being considered nuclear, of course, is a very, very, it's a very important asset that we don't want hackers to be able to get a hold of. And like going more from just like intrusion detection, which is what we see a lot of the existing software out there does. It looks for intruders that are sitting on the network. Denial of service attacks looks for those kinds of things. But it's really the application-specific faults like what happened with Stuxnet, where like the existing system started doing the wrong thing and nobody knew that it was doing the wrong thing until the uranium wasn't enriched. So like knowing your grid asset is doing the wrong thing because you know what it's supposed to do, and if it's acting contrary to that, like building in smarts using AI through understanding what the data is and how the assets behaved over time, to know that intruders actually made their way in through all of the defenses you want to put up. They've made their way in, and in the end, they're affecting the output of your asset. Being able to detect that because you know it's doing the wrong thing, I think is an area where a lot more people and a lot more companies need to spend more time.
Oh, that's awesome, which gives me one thought, and I'm giving Mark the last word. So, Mark, we're talking about nuclear energy. We're talking about AI. Tell us a little bit about the news we broke earlier this year.
Yeah, I was hoping I was going to get a chance to talk about it, but so we as well invest a lot in AI startups. We have an Inception program. It's got about 16,000 plus AI startups that we work with across industries. There's about 600 in energy, and one of them that we've started working with, thanks to the folks at PG&E, is Atomic Canyon, who basically has deployed a solution stack on-prem at Diablo Canyon to help them with their operations and maintenance and the work at that facility by taking a lot of the public data that's available through the NRC and through their manufacturers and all of that, and then building a model to help the workers at Diablo Canyon be much more efficient in how they manage that facility. And I think it's proven to be very successful already.
Yeah, and that's just scratching, we're just scratching
Absolutely.
the surface. And so I guess my message to all the Purdue researchers, engineers, students, I think we're broadcasting online right now. We want you to know the energy business could not be more exciting, and that we're just at the early ages of what is going to happen to what has been a very staid and steady industry for 80 to 100 years. It is a new era. It's a new dawn. Data science, analytics, AI are going to be essential. Systems, controls, sensors. It's a whole new era of energy and energy research, and we're so proud to be here at Purdue today to celebrate what the future looks like, and can't wait to keep doing better and smarter and faster with all the Purdue engineers. So thank you for having us today. Great to be with you.
Thank you.
Thank you.
Everyone, I'm over here. Like a true professor, I'm going to speak behind this AV card, like we do in the classroom. So, my name is Dionys Alibrantis, and I'm a professor in the Elmore Family School of Electrical and Computer Engineering. I'm also the chair of the Schweitzer Power Energy Systems area. I'm serving as a co-director of the Grid of Tomorrow Consortium with my colleague Andrew Liu, Professor Andrew Liu from Industrial Engineering. And thank you all for taking time out of your super busy schedule to travel to West Lafayette for this meeting. A colleague once told me that good things happen to those who show up. So I'm confident that showing up here today, braving the Indiana weather, which today wasn't that bad, will lead to a remarkable achievement, the founding of a new consortium between industry and academia with a mission to catalyze research and bolster workforce development to address the challenges in the rapidly changing electricity landscape. In the age of Zoom calls, there is something also to be said about some good old face-to-face interaction, a real handshake. We are here not only to discuss business, but to get to know each other better and build a certain level of trust that is necessary for moving this collaboration forward. The opportunity to take part in the creation of a unique consortium like this one does not come about every day. First, a huge thank you to Patty Poppy and everyone at PG&E for championing this initiative. Thank you to Schweitzer Engineering Labs for supporting our program over the years. Thank you to Dean Arvin Raman. Thank you to Professors Fabio Ribeiro and Lefteri Tsoukalas for leading the LEAPS initiative that positions Purdue at the forefront of the energy transition. And thank you to Professors Vasilis Kekatos, Junji Chin, Siva Sitharaman, and Xiaonan Lu, who were instrumental in making this happen. Finally, many thanks to Purdue College of Engineering staff for organizing this one-of-a-kind event. Now, I'm going to go a little off script because I have to acknowledge the tragedy that occurred last night in Washington, D.C. Having taken myself these late-night flights in and out of DCA, I was quite shocked to hear the news, and I hope that you're not going to confuse the lighthearted tone of these prepared remarks with a lack of empathy for the victims and their families. So you all must be exhausted from a long day of lab tours and panel discussions, and this is a cliche, but I do understand that I'm here, standing between you and a well-deserved dinner, and why not a few drinks at Harry's? So I'm going to begin by apologizing for reading from these prepared notes. I can guarantee to you that this is not how I deliver my lectures. I'm never this well prepared. And as a disclaimer, this presentation only reflects my personal thoughts and vision as these have developed over the last year or so. From the moment Andrew and I were thrust in our roles as co-directors of this consortium, we are hereby considering launching. And in our discussions tomorrow, we will be looking at you to help us determine how exactly this consortium will function. Now, this presentation is one of the most important and arguably the most intimidating I have ever delivered in my career. So in this moment of weakness, I admit I was tempted by the devil. I wanted to ask ChatGPT to help me write this speech. But I resisted, and for good reason, because you did not travel here to be treated with a regurgitation of canned concepts about pre-competitive research and the like. We see this consortium as something brand new and fresh, and I'm certain that no AI tool has ever encountered anything like this in its training. There we go. So earlier today, we heard from our distinguished panelists about challenges and opportunities associated with the energy transition. And I doubt it will be an effective use of our time to repeat those here. There will be plenty of time tomorrow to delve into these issues when we will attempt to come up with potential solutions moving forward. So if you would entertain me for a few more minutes, I would like to provide my perspective on, first, why the Grid of Tomorrow Consortium needs to be established now and here at Purdue, and second, how we could design it to have impact that is real, meaningful, and long-lasting. Now, by way of introduction, as you can likely guess by my first name and my admittedly weird accent, I'm an immigrant to this country. I was born and raised in Athens, Greece. And you may know Greece as the birthplace of democracy, theater, the Olympic Games, marathons, and home of the Parthenon. But you may not be aware of the many scientific discoveries related to power and energy that are attributed to the ancient Greeks. So first, Thales of Miletus in the 6th century BC, one of the 7 sages of antiquity, who was the first philosopher to conduct experiments with magnetism and static electricity. Democritus, who suggested in the 4th century BC that matter is made of atoms. Archimedes of Syracuse, who in the 3rd century BC harnessed the power of the sun to destroy an invading Roman fleet by burning their ships. Or Hieron of Alexandria, who invented the first wind turbine and the first steam engine in the 1st century AD. So you can probably guess where this is going. If you've seen the movie My Big Fat Greek Wedding, like the stereotypical Greek person that I am, I can't help myself from telling you that Greeks invented everything. We invented, as you saw, electromagnetism, atomic energy, solar energy, wind turbines, and many other things. And Windex. But as you know, unfortunately, the great scientific and engineering achievements of our ancestors were followed by the darkness of the Middle Ages. For 1,000 years, scientific progress stopped and innovation was stifled. So I'm using this historical metaphor because it also reflects what happened to power engineering education in the US, which experienced its own Middle Ages during the 80s and 90s, when attention shifted to other emerging areas like computers and communications. And in the grand scheme of things, this wasn't that bad after all, because this explains how we now have cell phones, the internet, social media, and AI. But the downside to this swing of the pendulum was that during this period, many power systems programs disappeared from academic institutions. Interest in the area declined, funding for research in electric power dried out, professors retired, electric machines and high voltage labs were dismantled. And even here at Purdue, the historic Purdue Electric Power Center, or PEPC, which had been founded in 1971, had become defunct by 1990. Interestingly, PG&E was a member of the center, as was NIPSCO, and several other utilities from the Midwest. And the decline of power engineering education has had a lot to do with the workforce shortage that this industry has been facing over the last 20 years. And we should not let this happen again, because power engineering, electric power engineering, is just too important. Thankfully, after the Middle Ages of the 80s and 90s, the electric power industry has been experiencing its own renaissance, spurred by the smart grid, the connection of renewables in unprecedented levels, the electrification of transportation. And today, the tsunami of artificial intelligence is revolutionizing literally everything, including how we plan and operate the power grid. So the answer to the why now question is abundantly clear. There is simply no time to lose, and we need to work with a sense of urgency and determination. Which brings me to the why Purdue question. I could answer this by laying out some cold facts about Purdue. We are now the largest producer of engineers nationwide. We are home to world-class faculty with cutting-edge research facilities and lab space. We boast some of the most highly ranked engineering programs with comprehensive curricula in person and online. But perhaps I could answer this more effectively by sharing my personal story. In the late 90s, I was a prospective graduate student, and I was eagerly looking for programs in the US to pursue my PhD, but I was utterly disappointed. There was no power program to speak of in places like Stanford, Berkeley, Caltech, UCLA, Harvard, Columbia, many other well-known universities. I was looking, as a student, for a comprehensive and vibrant academic program, which means one that could showcase a group of research-active faculty with expertise in power systems, electric machines, and power electronics, which are the three pillars of electric power engineering. So I enrolled at Purdue, which was one of a handful of schools that kept the power engineering flame going, or burning. So I'm a proud Purdue alumnus, like many of you in the audience today. And so using a Middle Age analogy again, Purdue was a monastery. And the monks who transferred their knowledge to us were legendary professors like Ahmed El-Abiad, Paul Krauss, Jerry Haidt, and Oleg Wazenchuk. So instead of asking ourselves, why Purdue, we should be exclaiming, why not Purdue? Now, of course, our rich history in power engineering alone is not sufficient. What will really drive the center forward is the present state of affairs at the university. So I have been a Boilermaker for a long time, but what has happened over the last 12 years under the leadership of two presidents, first Mitch Daniels and now Dr. Mang Chiang, is unprecedented. Because Purdue has culturally transformed itself from a university that was content in its role as an incredibly good engineering school to one that aspires to be a national leader in many initiatives like semiconductors and AI. And our motto is to become, excuse me, the pinnacle of excellence at scale, and this defines everything we do. Now, this transformation came with significant growth, not only in terms of numbers of students, but also in terms of faculty. And throughout the College of Engineering, today our expertise is exceptionally broad. A small subset of us has been engaged as the core team of faculty that helped develop this event. But there are many colleagues out there who work in relevant areas. The Grid of Tomorrow Consortium will harness this remarkable potential so that we can focus our energy on solving the most timely and important problems. Now, I'm always the first one to confess, humbly confess, that we professors are not omniscient creatures with superhuman capabilities. We are merely here to serve as mentors to our students, pointing the way based on our experience and instincts on what may or may not work. Our job is to provide the next generation with the knowledge and resources that will allow them to follow their dreams and aspirations. So I would say that by investing in this consortium, you are primarily investing in the creation of human capital. The energy transition needs an army of undergraduate and graduate students with a solid understanding of the fundamentals of electric power engineering and with an appreciation of the complexity of the challenges we are facing. Your return on investment would be people who see the amazing opportunity in this sector and who would want nothing else than a career in power engineering, and they would be ready to join the ranks in your companies and jump in the trenches for some serious and advanced technical work. To this end, we would like to establish what we call a Grid of Tomorrow Fellows program. For maximum impact, our best and brightest student researchers would spend their summers, as interns with you, where they would be embedded within your technical teams to see firsthand how things work, but also to start figuring out how they could be improved. And as you help us shape the details of the consortium tomorrow and in the coming months, you will have the opportunity to develop this fellows program to your liking. I suppose that another burning question is there room for a consortium in this space? And rephrasing this to address the elephant in the room, isn't this what the Electric Power Research Institute, or EPRI, is also doing? So let me be clear. EPRI is a great organization. Our colleagues at EPRI are amazing at what they do, and they have played and continue to play a key role in serving the needs of the electric power sector. And it would be madness to suggest that we are here to compete against EPRI. Our vision is to be 100% complementary to EPRI. As an academic institution, our research naturally happens at a lower, more fundamental level. In terms of technology readiness level, or TRL, which is a term that the Department of Energy really loves, you could say we work at TRL 1 or 2 through TRL 4 or 5 on a scale of 1 to 8. Here, we thrive in giving birth to new concepts and moving them to validation in the laboratory or in some relevant environment. On the other hand, EPRI and the vibrant ecosystem of companies that took part at the PG&E Innovation Summit tend to work at higher TRLs. So their products are meant for actual implementation and commercialization. But as much as I wish this were not true, inspiration is not something that comes on demand or through contractual agreements with rigid timelines. Archimedes said eureka after solving a difficult problem, showing us that inspiration can come at the most unexpected moment. However, as a prerequisite, you need to be in an environment that is conducive to thinking deeply, allowing time, plenty of time, to study, learn how others try to solve the same problem before, time to struggle with your different ideas, time to fail, time to understand why you failed. So I think we need effective mechanisms to spur innovation at the lower TRL level, TRLs, because of all the game-changing technologies that are rapidly reshaping the energy sector. The National Science Foundation even has a special name for this. They call it convergent research. This is the type of research that brings together various disciplines to tackle the most vexing and wicked problems. And I have a feeling that you're all here today because something inside you is telling you the same thing. Now, I just mentioned NSF, the National Science Foundation, so I feel obligated to say a few words about federally funded research and how we envision the Grid of Tomorrow Consortium to be different. NSF and DOE-funded research are noteworthy because of how they stimulate innovative multidisciplinary research. However, these grants are extremely difficult to get. And often, very good proposals are not funded. So essentially, what this means is that you have here the smartest people in the world, not me, others, working for hours to prepare a proposal for $1 million, say, with a rejection probability of 90%. Is this a good use of our resources as our society? Granted, some of this time goes on doing some technical work, but usually a major effort goes towards preparing a bunch of auxiliary proposal documents with an unpleasant bureaucratic aroma. And then, if you're lucky to be awarded the project, the continuous reporting and meetings can be overwhelming and stressful. So our vision is to be different from this operational model. We aspire to be fast and nimble so that we can go from research questions to funded projects as fast as humanly possible, and to operate leanly and efficiently with a sharp focus on the final objective. So think of how SpaceX operates, super fast, as they tenaciously pursue the ultimate goal of landing people on Mars. So the strategic doing workshop that we have planned for tomorrow aims to make the first step towards this convergence between industry and academia so as to get the consortium up and running within the next 3 months. Clearly, we're not here to provide you with turnkey solutions. Rather, we are at our finest developing mathematical algorithms, new theories, explaining how things work, writing pre-alpha code, and designing hardware prototypes. All of this is what one would call intellectual property. In fact, we generate so much IP daily that we don't know what to do with it. Some of it eventually makes its way through the Purdue Research Foundation IP disclosure process, and we're very good at doing that. But most of our ideas are archived in libraries, where they just collect dust. We are asking for your guidance to amplify our impact and to focus the minds of our brilliant students towards practicable solutions for real and important problems. Now, to be honest with you, investing in this effort means you are willing to take on some risk, and you're willing to play a little bit the long game. But if you're willing to be a little patient, you will see great return on your investment through the IP that our projects will generate, which you will be able to license with first rights if you join the consortium as a member. For more details about this, look out for Andrew's presentation tomorrow and the discussion we're going to have around lunchtime. So, as you probably understand even better than me, the main motivation for forming a consortium is to establish a mechanism for pre-competitive collaboration. So by joining the Grid of Tomorrow Consortium, you would be forming a partnership to address some of the shared problems in the power industry. Your resources would be pooled, and everyone would benefit from the research findings. However, I would like to note that this is not the only mode of collaboration possible. Being part of the consortium would not preclude you from establishing research projects directly with faculty, if this is something you would be interested in pursuing. Now, in my mind, and this is all in my mind, the Grid of Tomorrow Consortium could evolve to become one of 3 different types, loosely classified based on annual budget. Type A would be a more or less standard consortium with an annual budget of about $500,000. For example, the 1988 budget of Pepsi, the Purdue Electric Power Center, was $120,000. This amounts to $327,000 today. Pepsi had 15 industry members at the time. The funds were used to support 9 master's level students and a handful of undergrads. There is no indication that the projects of Pepsi were coordinated in any sense other than being loosely related to power engineering. Now, type B would be a larger consortium / research center with an annual budget of about $5 million. This would be sufficient for supporting, say, 30 master's and PhD students, their faculty supervisors, the salary of a director, administrative staff, and maybe there would be some funds left for purchasing lab supplies and equipment serving the needs of various projects. And type C would be a research center with an annual budget of, let's say, $20 million. This would be, of course, a substantially larger operation, not only in terms of numbers of students, faculty, and staff involved, but it would come with its own building, Dr. Rahman, and dedicated, we're working on that, dedicated laboratory space for a medium voltage, for medium voltage apparatus, switch gear, hardware in the loop capabilities, or even a mini data center. This type of center would be analogous to our own Herrick, Zucrow, or Bowen laboratories. And it would allow us to serve as a test bed for testing new technologies before their deployment to the field. Of course, this all depends on your appetite and is entirely up for discussion. But if I could request from you one thing, it would be to challenge us with a moonshot or a remarkably ambitious pursuit. In my opinion, this would be the most impactful consortium of all, regardless of the budget. I'm almost done, so please allow me to conclude these remarks by going back to my Greek heritage once more. So, the ancient Greeks invented fire itself. Yes, that's right. Remember that guy Prometheus, who gave fire to humans and then was punished by Zeus by being tied to a rock for eternity? But other than fire, we also invented wildfire. And now I'm dead serious. And every summer, my home country, Greece, is ravaged by wildfires. And our family house in Greece has been scorched repeatedly by wildfire. Others, regretfully, have not been so fortunate. In 2018, 104 people lost their lives in a beautiful coastal suburb of Athens, very similar to Malibu and Pacific Palisades, which burned to the ground from a wildfire that was impossible to contain on a day that was super violently windy. Here in the US, the death toll in the recent LA wildfires has reached 28 souls. And indeed, a single spark, as we say in Greece, is enough to cause a catastrophe. At the PG&E Innovation Summit last November, which I attended, I listened to Patty's personal story about the impact of California wildfires, and this has resonated deeply with me. The PG&E North Star goal to eliminate wildfires caused by power lines is truly inspiring. And I hope that this consortium can play a role in making this happen. So, finally, I'm going to show you Solon, another one of the 7 ages of ancient Greece, and the founder of Athenian democracy. In these 3 words that you cannot, I know you cannot read, but I'll translate to you shortly. Solon captured an entire philosophy and way of life. He said, every day, as I grow older, I always learn something new. That's what these 3 words mean. It would behoove us for this to be the overarching philosophy of the Grid of Tomorrow Consortium as well. Like I said earlier, we do not profess to be encyclopedias of knowledge. We are not here to sell you our research. We want to listen to your problems and to learn something new from each other each day. Let's do this. Thank you very much for your attention. Enjoy your dinner and see you tomorrow.